What if everything we thought we knew about the universe was just the tip of the iceberg? Picture this: scientists in labs around the world are witnessing phenomena so bizarre, they make time travel look like child's play. Light that defies its own speed limit, particles that whisper to each other across unimaginable distances, and black holes that might not be what they seem at all. These aren't scenes from a sci-fi movie. They're real experimental paradoxes tearing at the seams of Einstein's theory of relativity. And today, we're diving headfirst into 46 of the most mind-bending ones, each one a cosmic puzzle waiting to be solved. Think about the last time you felt that jolt of wonder, the moment you realized the universe is far stranger than you ever imagined. That's the feeling we're chasing here. Because these paradoxes aren't just academic curiosities, they're clues hidden in the fabric of reality itself, hinting at a physics we haven't even begun to understand. What happens when quantum particles, separated by light years, somehow mirror each other's actions instantly? Why do some experiments suggest time might not flow in just one direction? These questions don't just challenge Einstein's legacy, they could redefine the very laws governing existence. This isn't just a journey through abstract theories. It's an invitation to stand at the edge of human knowledge and peer into the unknown. Every paradox we explore today is a thread in a larger tapestry, one that connects the tiniest particles to the vast expanse of the cosmos. And the most thrilling part, you don't need a physics degree to join the adventure. All you need is curiosity. So buckle up. By the time we're done, you'll see the universe, and maybe even reality itself, in a whole new light. Einstein called it spooky action at a distance, that eerie connection where two quantum particles, no matter how far apart, seem to dance in perfect sync. But here's where things get truly bizarre. When scientists measure one particle, its entangled partner instantly responds, as if space between them doesn't exist. This isn't theoretical. Lab experiments have caught photons coordinating faster than light itself could travel between them, smashing relativity's golden rule that nothing outpaces light speed. Imagine flipping a coin in New York and another in Tokyo, landing heads up every single time you do, with no delay. That's entanglement in action, a phenomenon so counterintuitive it left even Einstein uneasy. The real shocker, this isn't just some microscopic oddity. Researchers have tested entangled particles separated by over 1,000 kilometers, and the results stay rock solid. The connection defies distance entirely. It's as if the universe has a hidden hotline, bypassing the speed of light entirely. Some theories suggest these particles might be tapping into extra dimensions, or that space-time itself is fundamentally interconnected like a cosmic web. Others wonder if relativity's speed limit only applies to the world we can see, while quantum particles play by different rules behind the scenes. What makes this paradox so explosive is that it doesn't just challenge Einstein, it forces us to rethink reality's very framework. Either locality, the idea that objects are only influenced by their immediate surroundings, is dead, or relativity isn't the whole story. And with cutting-edge quantum networks and unhackable encryption already leveraging entanglement, this isn't just philosophy. The universe might be far more mysterious and far more connected than we ever dared imagine. Now let's plunge into the cosmic abyss where relativity and quantum mechanics wage their fiercest battle, the black hole information paradox. Picture throwing a book into a fire. The pages burn, but in theory, if you could track every ash particle and wisp of smoke, you could reconstruct every word. Quantum mechanics insists information works the same way. It can't vanish, only scramble. But here's the catch. Einstein's equations say black holes erase information utterly. Once something crosses the event horizon, it's gone forever, crushed into a singularity where not even light escapes. Enter Stephen Hawking's bombshell discovery: black holes aren't entirely black. They slowly leak energy, now called Hawking radiation, evaporating over eons. At first glance, this seems like a way out. Maybe information hitches a ride on that radiation. But the math reveals a nightmare. Hawking radiation is random, like thermal noise from a heater. It carries no trace of what fell in. So where does the information go? Relativity says it's obliterated. Quantum mechanics says that's impossible. This stalemate sparked one of the wildest ideas in modern physics, the firewall paradox. What if the event horizon isn't the smooth gateway relativity describes, but a seething wall of quantum fury? Imagine approaching a black hole expecting empty space, only to smash into a Planck-scale inferno the instant you cross the horizon. It's a radical fix, suggesting Einstein's serene spacetime fractures at the quantum level. But here's the twist: firewalls violate relativity's core principle, the equivalence that says free fall feels like floating in empty space. The stakes couldn't be higher. If information escapes, it rewrites how we view causality. If it's destroyed, quantum theory needs an overhaul. And if firewalls are real, spacetime isn't the seamless fabric we thought. It's got trapdoors. Laboratories can't recreate black holes, but theorists are mining this paradox for clues, from holographic principles where information lives on the horizon's surface to wormholes linking entangled particles. Each solution feels like glimpsing the universe's blueprints, where relativity's rules warp under quantum pressure, revealing a reality far stranger than either theory predicted alone. Einstein's twin paradox is one of relativity's most famous mind-benders. Send one twin on a near light-speed journey, and they'll return younger than their Earth-bound sibling. But what if time doesn't just slow down predictably like relativity claims? Modern experiments are uncovering wrinkles in this classic tale. Take atomic clocks flown on high-speed jets. They do tick slightly slower, just as Einstein predicted. Yet when scientists peer into the quantum realm, things get murky. Quantum clocks existing in superposition, meaning they're in multiple states at once, don't always follow relativity's rulebook. Sometimes they seem to experience time ambiguously, as if the flow itself becomes fuzzy. This isn't just a technical hiccup. It suggests time might not be the rigid, universal river we assume. Imagine two stopwatches, one on a rocket, one on Earth. Relativity says the rocket's watch runs slower, and that's that. But quantum clocks behave like they're straddling multiple timelines, with no clear answer to how much slower. It's as if time, at the smallest scales, hesitates, refusing to commit to a single speed. Some theorists argue this blurriness hints at a deeper layer of physics, where relativity and quantum mechanics clash over time's true nature. Here's where it gets even stranger. Recent lab experiments with entangled quantum clocks show pairs of particles influencing each other's timekeeping instantaneously, defying locality just like entanglement does with position or spin. If time itself can be entangled, does that mean the past, present, and future are more fluid than relativity allows? Or could there be hidden dimensions where time operates differently, leaking into our reality in these paradoxical ways? The twin paradox was meant to showcase relativity's elegance. Now it's becoming a battleground. Either relativity needs tweaking to account for quantum time quirks, or we're missing a fundamental piece of the puzzle, one where time isn't just stretched or squeezed, but fundamentally unsettled. And with quantum computers and GPS satellites relying on ultra-precise timekeeping, this isn't just theoretical. The universe's clock might be ticking in ways Einstein never dreamed of. Einstein once scribbled a term in his equations called the cosmological constant, a fudge factor to keep the universe static, as everyone assumed it was. He later called it his greatest blunder when the universe turned out to be expanding. But now that so-called blunder is back with a vengeance, and it's weirder than anyone imagined. Because the universe isn't just expanding, it's accelerating, racing apart faster and faster, as if some invisible hand is pressing hard on the cosmic gas pedal. Scientists call this phantom force dark energy, and it makes up a staggering 68% of the universe's total energy. Yet here's the kicker: relativity's equations can't explain where this energy comes from or why it behaves this way. Think of it like tossing a ball in the air, expecting it to slow down and fall back only to watch it shoot upward faster and faster, defying gravity entirely. That's the universe we live in. Einstein's cosmological constant was meant to balance gravity's pull, but dark energy doesn't just balance it, it overpowers it completely. Some researchers argue this means relativity, while flawless in our solar system, might crack under the weight of the cosmos. Could gravity itself change over vast distances? Modified gravity theories, like MUND, suggest that on galactic scales, Newton and Einstein's rules warp, producing effects we've mistakenly blamed on dark matter and energy. But there's another twist. Quantum physics predicts that empty space should bubble with energy particles flickering in and out of existence. If you add up all that energy, you'd expect a cosmological constant 120 orders of magnitude larger than what we observe. That's like predicting an ocean and finding a single drop. This mismatch is so colossal, it's been called the worst theoretical prediction in science. So here we stand, caught between two impossibilities. Either relativity is incomplete, missing some cosmic correction that tames quantum vacuum energy, or dark energy is something entirely foreign, a new force or dimension bending the universe in ways we can't yet fathom. Telescopes like Euclid and the Vera Rubin Observatory are scanning the skies for clues, hunting for tiny ripples in space-time that might reveal dark energy's secrets. One thing's certain: Einstein's equations, once the unshakable foundation of cosmology, are now a frontier, and the universe is daring us to look deeper. In 1972, NASA Pioneer 10 spacecraft embarked on a one-way journey beyond our solar system, only to stumble into a cosmic mystery that still baffles physicists today. As the probe ventured past Jupiter, something bizarre happened. It began slowing down ever so slightly, as if an invisible hand were tugging it backward. Not by much, just a fraction of a nanometer per second squared, but enough to throw Einstein's pristine equations into question. By the time Pioneer 11 followed suit, the anomaly was undeniable. Both probes were decelerating in ways relativity couldn't explain. At first, scientists scrambled for conventional answers. Maybe heat radiating unevenly from the spacecraft's power systems was nudging it off course, like a tea kettle steaming itself sideways. Yet, even after painstakingly modeling every bolt and antenna, the numbers refused to add up. The discrepancy persisted, a tiny but stubborn glitch in gravity's grand symphony. Then came the real shocker. When researchers crunched the data, they found the deceleration matched a peculiar pattern. It was as if the probes were responding not just to the sun's gravity, but to something deeper, a force proportional to their speed through space itself. This opened the floodgates to radical theories. Could inertia, the resistance of objects to changes in motion, be more complex than Newton or Einstein imagined? Modified inertia models like physicist Mordechai Milgram's suggested that in the icy quiet of deep space far from galaxies' pull, gravity's rules might subtly shift. Others wondered if dark matter's unseen tendrils were snagging the probes, or if relativity itself needed tweaking at the solar system's edge, but the plot thickens. Recent missions like New Horizons racing toward interstellar space haven't shown the same slowdown. Was Pioneer's anomaly a fluke, or are we missing a crucial variable? Some speculate the probe's unique spin-stabilized design, tumbling like a slow-motion bullet, interacted with spacetime in ways modern box-shaped spacecraft don't. Others propose a far wilder idea, that gravity's strength isn't perfectly constant, but fluctuates on scales we've yet to measure. The Pioneer anomaly is more than a technical hiccup. It's a whisper from the void, hinting that our cosmic neighborhood might hide secrets relativity hasn't accounted for. Whether it's unseen physics or a still-hidden quirk of engineering, one thing's clear. The farther we reach into space, the more the universe reminds us how much we have left to learn. Quantum mechanics tells us the vacuum of space isn't empty. It's a seething ocean of energy, with particles flickering in and out of existence so fast we can't detect them directly. These quantum fluctuations should fill every cubic centimeter of space with unimaginable energy, warping space-time so violently that the universe would either curl into a tiny ball or explode outward in seconds. Yet when we look up at the night sky, the cosmos is eerily calm. The curvature of space-time is nearly flat, as if all that chaotic energy simply isn't there. This isn't just a small oversight. Quantum theory's prediction of vacuum energy overshoots reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the largest mismatch in all of science. So where does all that energy go? One possibility is that hidden dimensions, curled up at scales too tiny to observe, are absorbing the excess. Imagine blowing up a balloon with a microscopic pinhole. Most of your breath inflates it, but a tiny fraction escapes unseen. Similarly, extra dimensions predicted by string theory might be siphoning off vacuum energy, leaving just a faint residue in our observable universe. Another wild idea involves an undiscovered field that counteracts quantum energy perfectly, like a cosmic thermostat dialing the vacuum's intensity down to nearly zero. But the plot thickens. Dark energy, the force accelerating the universe's expansion, behaves as if it's fueled by a faint vacuum energy. The catch: its measured value is still 60 orders of magnitude weaker than quantum predictions. It's like expecting a hurricane and feeling only a breeze, yet that breeze is somehow pushing galaxies apart. Some theorists argue this isn't a coincidence, that dark energy and the vacuum catastrophe are clues to a deeper symmetry, one where the universe naturally cancels out most vacuum energy, leaving behind just the faintest whisper. The stakes couldn't be higher. If relativity and quantum mechanics can't agree on something as fundamental as empty space, it suggests one or both theories are missing a critical piece. Experiments like the Casimir effect, where metal plates placed micrometers apart feel a tiny force from quantum fluctuations, prove vacuum energy is real. Yet its weakness on cosmic scales remains physics' greatest unsolved puzzle. Whether the answer lies in extra dimensions, new fields, or a revolutionary tweak to Einstein's equations, one thing's clear: the void isn't empty. It's a battlefield where our best theories clash, and the outcome could rewrite reality itself. In 2011, physicists at the Opera experiment made a claim so shocking it sent ripples through the scientific community. Neutrinos, those ghostly particles that barely interact with matter, appeared to be breaking the universe's ultimate speed limit. Their measurements suggested these particles had outpaced light by a hair's breadth, arriving at their detector 60 nanoseconds sooner than relativity allowed. For a brief, electrifying moment, it seemed Einstein's century-old theory might finally have met its match. Headlines blared about the death of relativity, while physicists scrambled to reconcile the impossible. But here's where the story twists. The anomaly wasn't caused by some revolutionary new physics. It traced back to something far more mundane, a loose fiber optic cable. A faulty connection had skewed the timing measurements, and once fixed, the neutrinos fell back in line with relativity's predictions. Yet this wasn't just an embarrassing blunder. It revealed something deeper about how science grapples with the unknown. The opera team had meticulously checked their results for months before announcing them, embodying science's self-correcting nature. Even when chasing shadows, the process works. What's fascinating, though, is that the ghost of this anomaly lingers. Other experiments, like MINOs in the United States and T2K in Japan, have occasionally recorded neutrinos behaving just a little too fast, though never definitively. These tiny discrepancies live in the margin of error, statistical maybes rather than certainties, but they've sparked a tantalizing question. What if neutrinos, under certain conditions, can flirt with superluminal speeds? Some theories suggest these particles might take shortcuts through extra dimensions or interact with undiscovered fields that tweak their effective speed. Others propose that neutrinos, unlike photons, don't feel spacetime's friction in quite the same way. The real lesson here isn't just about faulty cables or statistical noise. It's about the boundaries of our knowledge. Relativity has withstood a century of tests, but neutrinos, nearly massless, barely detectable, and endlessly mysterious, keep nudging at its edges. Whether these anomalies are measurement quirks or hints of deeper physics, they remind us that the universe still holds cards it hasn't shown, and for scientists, that's the most thrilling possibility of all. Einstein, Podolsky, and Rosen thought they'd found the fatal flaw in quantum mechanics, a crack in the theory so glaring it would force physicists back to the drawing board. Their famous EPR paradox, laid out in 1935, hinged on the absurdity of quantum entanglement. Two particles, once linked, could instantaneously influence each other's properties across any distance, no matter how vast. To Einstein, this spooky action at a distance was unthinkable, violating relativity's sacred rule that nothing, not even information, could outpace light. He was convinced quantum mechanics had to be incomplete, missing hidden variables that would restore sanity to the universe. But the universe had other plans. Decades of experiments, from Alain Aspect's pioneering work in the 1980s to recent loophole-free tests, have delivered the same verdict: entanglement is real. Measure one particle's spin, and its partner snaps into the opposite state instantly, as if space between them doesn't exist. The kicker: this happens even when the particles are separated by distances so large that light itself wouldn't have time to carry a signal between them. It's not just that Einstein was wrong, it's that reality itself seems to play by rules he never anticipated. So where does that leave relativity? If entanglement defies locality, the idea that objects are only influenced by their immediate surroundings, then maybe spacetime isn't the fixed, orderly stage Einstein envisioned. Some theorists now speculate that quantum non-locality hints at a deeper layer of reality, where particles are fundamentally interconnected in ways that transcend space and time. Imagine the universe as a vast hologram where every part contains information about the whole. Or picture spacetime as a network of quantum threads, with entanglement stitching it together behind the scenes. The most radical implication: relativity might not be the final word on how the cosmos operates. It works flawlessly for planets, stars, and galaxies, but at the quantum scale, it could be like using Newton's laws to describe a black hole, close but missing the mark. This doesn't mean Einstein's theory is wrong. It's more like discovering that the rules of chess don't apply to Go. Both games are valid, they just operate on different levels. What's thrilling is that this paradox isn't just philosophical, it's fueling real-world breakthroughs. Quantum computers leverage entanglement to perform calculations impossible for classical machines. Cryptographers use it to create unhackable communication networks. Each application is a test, probing the boundaries between quantum weirdness and relativistic order. And as the experiments grow more precise, one thing becomes clear: the universe is far stranger and far more connected than even Einstein dared to dream. Imagine a clock that never winds down, a structure that keeps perfect time forever without batteries, springs, or any energy input at all. That's the mind-bending reality of time crystals, a phase of matter so strange it seems to rewrite the rules of physics. First proposed in 2012 by Nobel laureate Frank Wilczek, these structures don't just exist in space like ordinary crystals, they repeat in time, oscillating between states with clockwork precision, even in their ground state where all energy is theoretically exhausted. It's like finding a pendulum that never stops swinging, long after the initial push has faded to silence. At first glance, this appears to violate one of physics' most sacred principles, the conservation of energy. If nothing's powering the motion, where's the energy coming from? Relativity, built on the assumption that time is uniform and symmetric, struggles to explain how these crystals break time translation symmetry, the idea that the laws of physics stay the same at every moment. Einstein's framework treats time as a smooth, flowing river, but time crystals suggest the river might have hidden whirlpools, places where time loops back on itself at the microscopic level. The real breakthrough came when researchers actually built them. In 2017, teams at Harvard and the University of Maryland created time crystals using chains of trapped ions and diamond defects chilled to near absolute zero. These systems, when gently nudged by lasers, began flipping between states at fixed intervals, like a metronome ticking without being wound, the kicker. This rhythm persisted indefinitely, immune to entropy's usual decay. It wasn't perpetual motion in the classic sense. The crystals weren't generating energy. Instead, they discovered a loophole in quantum mechanics, a way to lock motion into the fabric of matter itself. What does this mean for relativity? Time crystals hint that time might not be the passive backdrop Einstein envisioned. Instead, it could emerge from deeper quantum processes with microscopic structures influencing its flow. Some theories suggest these crystals are tapping into a quantum phenomenon called many-body localization, where particles become stuck in certain configurations, allowing collective motion without energy dissipation. Others propose their evidence of hidden temporal order, like frozen ripples in the fabric of time. The implications are staggering. If time can crystallize, it might mean our universe has layers of temporal structure we've never noticed, like invisible gears ticking beneath reality's surface. Already, researchers are exploring time crystals for quantum computing, where their stability could protect fragile qubits from decoherence. Others wonder if they're the key to understanding time's arrow, or even the early universe's conditions. One thing's certain: Einstein's elegant spacetime continuum might be just the first chapter in a much weirder story, one where time itself can freeze, pulse, and perhaps even shatter. The Hubble tension isn't just a minor discrepancy, it's a full-blown cosmic showdown. Picture two teams of astronomers, each armed with cutting-edge tools, measuring how fast the universe is expanding. One group studies the afterglow of the Big Bang, the cosmic microwave background, using relics from the universe's infancy to calculate its growth. Their answer: roughly 67 kilometers per second per megaparsec, meaning for every 3 million light-years you look deeper into space, galaxies appear to recede 67 kilometers faster each second. But here's where the plot thickens. Another team peers at pulsating stars called Cepheids, an exploding supernova in the nearby universe, and their measurements land closer to 73. That 6-kilometer gap might sound trivial, but in cosmology, it's a chasm. Statistically, the odds of this being a fluke are less than 1 in a million. So why does this rift matter? Because relativity ties the universe's expansion directly to its contents. The mix of dark energy, dark matter, and ordinary matter that shapes spacetime's fabric. If two gold standard methods disagree on how fast space is stretching, it's like baking the same cake with identical recipes and getting different results. Either we're missing an ingredient or the recipe itself is flawed. Some theorists argue this tension points to exotic dark energy that grows stronger over time, warping expansion rates unpredictably. Others propose early dark energy, a mysterious force that briefly surged during the universe's first 300,000 years, leaving a fingerprint that skews our measurements. But the boldest ideas go even further. Could relativity's equations need a cosmic tune-up? Modified gravity theories suggest that Einstein's description of space-time, while flawless in our solar system, might fray at the edges of the observable universe. Imagine gravity weakening slightly over vast distances, like a stretched spring losing its pull. Alternatively, what if dark matter isn't a single particle but a zoo of particles, some interacting in ways that alter large-scale expansion? The stakes are sky-high. Telescopes like JWST are now scrutinizing Cepheids and supernova with unprecedented precision, while next-generation observatories prepare to map the cosmic microwave background in finer detail. Each new dataset either deepens the mystery or inches us closer to a revolution. One thing's certain, the Hubble tension isn't just a problem to solve, it's a doorway. Behind it could lie entirely new physics, waiting to redefine our understanding of spacetime itself. Einstein's equivalence principle is one of relativity's cornerstones, the idea that standing still in Earth's gravity feels identical to accelerating through space in a rocket. But dive into the quantum realm, and this elegant symmetry starts to fray at the edges. Meet the Unruh effect, a bizarre phenomenon where an observer hurtling through empty space at breakneck acceleration would see a bath of glowing particles, while someone floating peacefully detects only darkness. It's as if motion itself conjures heat from nothing, transforming the vacuum into a thermal sauna. This isn't just theoretical, it suggests that relativity might be blind to quantum thermodynamics, a blind spot with staggering implications. Picture this, you're in a spaceship, engines screaming as you accelerate faster and faster. Outside your window, the void should look empty, but according to quantum field theory, your motion would warp the vacuum into a sea of virtual particles, glowing with heat proportional to your acceleration. To you it feels real, a warm, particle-filled universe, yet a nearby astronaut drifting at constant speed sees none of it. The same patch of space, observed differently, becomes either a furnace or an icy void. This isn't a measurement quirk, it's a fundamental clash between how relativity treats motion and how quantum fields respond to it. The real puzzle, the Unruh effect, implies that particles, and even temperature, aren't absolute. They're artifacts of perspective shaped by how you move. Einstein's equivalence principle insists that acceleration and gravity are indistinguishable, but what happens when acceleration also creates heat? Does gravity do the same? Some theorists argue that black holes' infamous Hawking radiation might be the gravitational cousin of the Unruh effect, with spacetime's curvature playing the role of acceleration. If true, it would mean empty space isn't just flexible, it's alive with quantum energy that flickers into existence depending on how you're moving. Testing this effect isn't easy. The temperatures involved are minuscule unless you're accelerating at unimaginable rates. Think a billion trillion times Earth's gravity. But physicists are getting creative. Ultra-fast electrons whipped around in particle accelerators might soon reveal hints of UNRWA radiation. Others are designing quantum probes that vibrate at near light speed, hoping to catch the vacuum's phantom glow. The stakes: if the UNRWA effect is confirmed, it could force a rewrite of how relativity handles quantum fields, bridging the gap between Einstein's smooth spacetime and the seething quantum foam beneath it. What's thrilling is that this paradox doesn't just challenge theory, it blurs the line between reality and perspective. If motion conjures particles from nothing, does that mean existence itself is a kind of illusion, dependent on how fast you're going? Or is the universe subtly layered, with quantum thermodynamics hiding in plain sight, waiting to reshape our understanding of acceleration, gravity, and the nature of empty space? The answers might lie in the quiet hum of a particle beam, or the glow of a vacuum that isn't as empty as it seems. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those numbers, the Milky Way alone should be teeming with civilizations, so where is everyone? This is the Fermi paradox in a nutshell, but when you bring relativity into the mix, the mystery deepens. Einstein's theory tells us that while light speed is an unbreakable barrier, time dilation offers a loophole. A spacecraft traveling close to light speed could cross the galaxy in what feels like decades for its crew, even as millennia pass on Earth. So why, in a universe where interstellar travel is theoretically possible, does the cosmos seem so silent? One answer might lie in relativity itself. The same time dilation that makes interstellar travel plausible for astronauts also makes coordination between civilizations nearly impossible. Imagine a starfaring society sending ships to neighboring stars. Even at 99% light speed, the crew might return to a homeworld that's aged centuries or millennia. Communication breaks down. Messages sent back to Earth would take just as long to arrive, rendering real-time conversation meaningless. The galaxy could be filled with civilizations, each trapped in their own temporal bubbles, unable to synchronize their existence. Then there's the energy problem. Relativity tells us that as you approach light speed, the energy required to accelerate grows exponentially. To reach even a fraction of light speed requires staggering amounts of fuel, far beyond what any civilization could feasibly produce without dismantling entire planets. Some theorists argue this is the Great Filter, not some cataclysmic event, but the simple, brutal physics that makes interstellar travel so impractical that civilizations inevitably turn inward, choosing virtual worlds over the void. But the most haunting possibility is that relativity's constraints aren't the obstacle, we are. Human minds evolved to think in terms of decades, not millennia. The idea of launching probes that might not reach their destinations for 100,000 years feels absurd to us. Yet what if other civilizations operate on entirely different timescales? Beings with lifespans measured in millennia, or machine intelligences with no biological urgency, might see interstellar travel as a routine, patient endeavor. If they're out there, they could be moving at a pace we can't even comprehend, their signals and ships drifting through the cosmos on timescales that render them invisible to our fleeting attention. Or perhaps the answer is darker. Relativity ensures that any civilization advanced enough to visit us would also be advanced enough to destroy us. The silence of the cosmos might not be a limitation of physics, but a warning, a cosmic game of hide and seek where the first to reveal themselves are the first to perish. The universe could be a vast, quiet forest with every civilization holding its breath, afraid to make a sound. The Fermi paradox, when viewed through relativity's lens, stops being a question of distance and becomes one of time, energy, and existential risk. It forces us to confront not just whether we're alone, but whether the universe is built to keep us that way, and that might be the most unsettling paradox of all. Einstein's equations contain a tantalizing loophole, one that could make warp drives a reality without breaking the universe's speed limit. The Al-Cubier drive, proposed by physicist Miguel Al-Cubier in 1994, exploits relativity's flexibility. Instead of moving through space faster than light, it contracts spacetime in front of a ship and expands it behind, creating a bubble that rides the cosmic fabric like a surfer on a wave. Inside this bubble, the ship remains stationary relative to its local space, avoiding relativity's ban on superluminal motion. No acceleration, no time dilation, just a smooth glide to the stars. But there's a catch that sends physicists into a tailspin. The drive requires negative energy, a substance that defies everything quantum mechanics tells us about how energy behaves. Negative energy isn't just rare, it's theoretically forbidden in large quantities. Quantum fields allow for fleeting negative energy densities, like tiny bubbles of repulsive gravity that pop in and out of existence. But the Al-Cubier drive would need oceans of it, sustained and stable, to warp spacetime enough for practical travel. The math says it's possible, quantum field theory says it's nonsense. This isn't just an engineering hurdle, it's a fundamental clash between relativity's spacetime gymnastics and quantum mechanics' ironclad energy rules. Here's where the paradox tightens. If negative energy can't exist in the amounts needed, does that mean relativity is silently permitting impossible technologies, like a car manual that includes instructions for flying? Or is Einstein's theory missing a hidden constraint, some quantum safeguard that prevents spacetime from being twisted into a warp bubble? Some researchers argue that quantum inequalities, mathematical limits on how much negative energy can exist in one place, act as cosmic traffic cops, ensuring no one cheats the speed limit. Others propose exotic workarounds, like harnessing dark energy's repulsive force, or tapping into higher dimensions where the rules might be different. The stakes are cosmic. If the Al-Cubier drive's energy problem is insurmountable, it could mean relativity and quantum mechanics are fundamentally incompatible when pushed to extremes, a fracture in physics' foundation. But if solutions exist, even in theory, they might reveal hidden layers of spacetime structure or new forms of energy waiting to be discovered. Laboratories are already testing microscopic analogs of warp effects using metamaterials and superconducting circuits, probing whether spacetime's fabric can be manipulated on human scales. What makes this paradox so thrilling is that it's not just about faster-than-light travel. It's a stress test for our deepest theories, forcing them to confront each other in uncharted territory. Whether the Al-Cubier drive remains science fiction or becomes science fact, its energy dilemma is a beacon, one that illuminates how much we still don't understand about the universe's rulebook and how bending spacetime might require rewriting physics itself. At the heart of every black hole, relativity paints a nightmare scenario, a singularity where matter crushes into an infinitely dense point, spacetime curvature spiraling toward infinity. Einstein's equations demand it. Once an object crosses the event horizon, there's no stopping its collapse into this cosmic dead end. But infinity isn't just a mathematical oddity. It's a flashing red warning sign that physics has lost its grip. Because in the quantum realm, infinities don't exist. Particles can't occupy zero volume. Energy can't spike without limit. So when these two titanic theories collide at the singularity, the universe hands us a paradox with no easy resolution. This is where loop quantum gravity steps in, offering a radical escape hatch. Imagine the singularity not as a pinprick of infinite density, but as a quantum foam, a turbulent sea where space-time itself becomes granular, like pixels on a screen. At scales a trillion times smaller than an atom, the smooth continuum of relativity shatters into discrete loops, preventing the infinite collapse. Instead of a singularity, you'd hit a quantum bounce, a cosmic trampoline where compressed spacetime recoils, possibly birthing a new universe. It's as if the black hole's heart hides a secret door, leading somewhere entirely unexpected. String theory takes a different approach, replacing the singularity with a fuzzy, vibrating tangle of multidimensional strings. Picture a guitar string stretched to its limit. Instead of snapping, it hums at higher frequencies, its energy dissipating into hidden dimensions. In this view, the singularity isn't a point but a dense knot of vibrating energy, blurring the line between matter and space-time. The fuzzball conjecture suggests black holes might be more like cosmic thistles, their interiors bristling with quantum complexity rather than geometric simplicity. What's revolutionary here isn't just the alternative to infinity, it's the implication that singularities are illusions, artifacts of relativity's blind spot at microscopic scales. If loop quantum gravity or string theory is correct, black holes might not be the ultimate in points we thought. They could be transformers, recycling matter and energy into new forms. Some models even suggest these quantum corrections could leave fingerprints, subtle echoes in gravitational waves, or distortions in the shadow of a black hole's event horizon. Yet the paradox lingers. If singularities don't exist, why does relativity predict them so confidently? The answer might lie in scale. Just as Newton's laws work perfectly for baseballs but fail for atoms, relativity could be a cosmic approximation, accurate everywhere except where quantum gravity takes over. The singularity, then, isn't a flaw in Einstein's math, but a boundary where his theory hands the baton to something deeper. Experiments are inching closer to testing these ideas. Gravitational wave observatories like LIGO are listening for hints of quantum structure in black hole mergers. Telescopes like the Event Horizon Telescope, which captured the first image of a black hole's shadow, might one day detect anomalies around the event horizon that betray what's happening inside. Each observation is a potential Rosetta Stone, decoding the language of quantum gravity written in the distortions of space-time. The singularity paradox forces us to confront the limits of our theories and the audacity of the universe. Whether it's loops, strings, or some yet unknown framework that resolves the infinite, one thing's clear. The darkest corners of the cosmos might be where physics shines its brightest, revealing secrets not just about black holes, but about the nature of reality itself. What if everything you see, touch, and experience is nothing more than an elaborate cosmic mirage? The holographic principle takes this sci-fi-sounding idea deadly seriously, proposing that our three-dimensional universe, with its galaxies, black holes, and swirling nebulae, might be nothing more than a projection of information encoded on a distant two-dimensional surface. Imagine the universe as a movie screen, where the vivid images of stars and planets are just shadows cast by data etched onto the screen's flat surface. This isn't just a metaphor, it's a radical challenge to Einstein's vision of spacetime as a smooth, continuous fabric. The roots of this paradox stretch back to black holes. When an object falls into a black hole, relativity says it's lost forever, vanishing into the singularity. But quantum mechanics insists information can't be destroyed. The holographic principle emerged as a solution. Perhaps the information isn't lost, it's smeared across the black hole's event horizon like ink on a balloon, preserved in two dimensions. Expand that idea to the entire cosmos, and you get a staggering possibility. Our 3D reality might be painted onto the universe's outer boundary, with every event inside merely a reflection of data stored at the edge. Here's where relativity bristles. Einstein's equations treat spacetime as a dynamic but smooth entity, bending and warping like rubber. The holographic principle, though, implies spacetime is pixelated at the tiniest scales, built from indivisible bits of information, like a digital image that looks seamless until you zoom in and see the pixels. If true, this means relativity's elegant geometry is an approximation, a low-resolution snapshot of a deeper, more intricate reality. Experiments are already hunting for clues. Gravitational wave detectors like LIGO could one day spot faint noise in spacetime's fabric, a potential signature of this underlying granularity. Meanwhile, quantum computers simulate holographic universes in miniature, testing whether 2D systems can generate 3D behaviors. The results so far are tantalizing. Certain quantum systems do behave as if they're projections of lower dimensional counterparts. But the most mind-bending implication isn't just about pixels or dimensions, it's about reality itself. If the holographic principle holds, then free will, consciousness, and even time might be emergent phenomena, illusions generated by the way information interacts on that distant 2D surface. It's as if we're characters in a video game, convinced we're making choices while somewhere outside the screen, code dictates every move. Einstein once dismissed quantum entanglement as spooky. The holographic principle takes that spookiness to cosmic levels, suggesting the universe itself might be the ultimate illusion, a shadow play written in quantum bits. Whether this paradox unravels relativity or reveals its hidden depths, one thing's certain: the line between science and philosophy has never been thinner. Imagine a universe where simply watching a pot could stop it from boiling, where observation alone has the power to freeze reality in place. This isn't some twisted fairy tale. It's the quantum Zeno effect, a phenomenon so counterintuitive it makes time itself seem malleable. Named after the ancient Greek philosopher Zeno, who famously argued that motion is an illusion, this effect reveals something startling. The act of measuring an unstable particle over and over can effectively halt its decay, as if time has paused for that particle alone. In labs, scientists have seen radioactive atoms stubbornly refuse to break down when monitored intensely, clinging to existence against all odds. It's as if the universe, under scrutiny, hesitates to change. Relativity paints time as a smooth, unbroken river, flowing at the same steady pace for everyone, everywhere. Einstein's equations treat it as a continuous dimension, woven seamlessly into spacetime's fabric. But the quantum Zeno effect suggests time might have a graininess to it, tiny, indivisible moments where reality refreshes like frames in a film. Each observation resets the clock, forcing the particle to decide again whether to decay. If these pauses add up, the particle never gets a chance to transition, trapped in a perpetual present. This isn't just a quirk, it's a direct challenge to relativity's assumption that time is infinitely divisible. The paradox deepens when you consider what observation really means in quantum mechanics. It doesn't require a conscious observer, just interaction with the environment, like a photon bouncing off the particle. In that instant, the particle's wave function collapses, resetting its decay probability. Some interpretations argue this isn't about time at all, but about information. Frequent measurements prevent the system from evolving into a state where decay is possible. Others see it as evidence of time's quantum structure, where the universe operates in discrete ticks too small for relativity to capture. Here's where Einstein's clockwork universe starts to falter. If time can be manipulated so easily at the quantum level, what does that mean for black holes, gravitational waves, or the cosmic expansion phenomena where relativity's smooth time is foundational. Could spacetime itself be pixelated, with a Zeno effect revealing the pixels? Experiments with trapped ions and superconducting qubits are testing these limits, probing whether continuous time is just an emergent illusion from deeper quantum processes. The most tantalizing possibility, this effect might not be limited to particles. Hypothetically, a system as complex as a human brain, though far harder to isolate, could, in theory, experience time differently under constant observation. While that's speculative, it underscores the stakes. If time isn't what relativity claims, our understanding of causality, aging, even the universe's fate might need rewriting. The quantum Zeno effect doesn't just freeze particles, it freezes our assumptions, forcing us to confront the unsettling idea that time, at its core, might be as fragile as a quantum superposition. What if gravity isn't a fundamental force at all, but something far stranger? An illusion conjured by the universe's hidden quantum connections. The emergent gravity hypothesis flips Einstein's spacetime on its head, suggesting that what we perceive as gravity might actually be a side effect of quantum entanglement's intricate web. Picture a vast cosmic tapestry where every particle's fate is secretly tied to every other, not through the warping of spacetime, but through invisible threads of quantum information. The curvature of space, the orbits of planets, even the pull of black holes, these could all be shadows cast by something deeper, something entanglement built behind the scenes. This idea didn't come from nowhere. In 2010, physicist Eric Verland proposed a radical rewrite of gravity's origins, inspired by an unexpected source, thermodynamics. Just as heat emerges from the chaotic motion of atoms, Verland argued, gravity could emerge from the way quantum information organizes itself across the universe. Think of spacetime as the surface of a lake. What looks like a solid plane is really the net effect of countless water molecules interacting below. In this view, Einstein's relativity isn't wrong. It's just the tip of an iceberg, a macroscopic approximation of quantum entanglement's microscopic dance. The implications are staggering. If gravity emerges from entanglement, it could explain dark matter's elusive nature without invoking invisible particles. Galactic rotation curves, which baffle astronomers because stars orbit faster than visible matter predicts, might instead reflect quantum information's distribution across space. It's as if the universe has been playing a shell game, hiding gravity's true source in plain sight. Some simulations already show promise entanglement-based models reproduce galactic behavior eerily well, no dark matter required. But here's where relativity pushes back. Einstein's equations treat gravity as spacetime's geometry, a smooth curvature shaped by mass and energy. If gravity emerges from quantum bits, why does relativity work so flawlessly from planets to pulsars? Supporters of emergent gravity argue it's like fluid dynamics. Water obeys equations that don't reference individual molecules, yet those molecules are the real foundation. Similarly, relativity could be the fluid approximation of a deeper quantum reality. The real test lies in the extremes. Black holes, where quantum gravity's effects should dominate, might reveal cracks in Einstein's framework. If entanglement fuels gravity, then black hole event horizons where information gets scrambled should behave differently than relativity predicts. Experiments like the Event Horizon Telescope could one day spot these deviations, hunting for anomalies in the shadows of black holes. Whether emergent gravity unseats relativity or simply deepens it, one thing's certain: the universe loves a good magic trick. What feels like the relentless pull of gravity might really be the whisper of countless quantum connections, weaving the fabric of reality from the bottom up. And if that's true, then Einstein's masterpiece wasn't the final word, just the first glimpse of a far weirder truth. Imagine waking up one day, convinced you've lived a full life, only to realize you're nothing more than a fleeting spark in the void, a self-aware accident conjured by random quantum noise. That's the nightmare scenario of the Boltzmann brain, a paradox so unsettling it makes the Matrix seem cozy. Named after physicist Ludwig Boltzmann, who first grappled with the statistical nature of entropy, this thought experiment suggests something bizarre. Given enough time, the random jostling of particles could spontaneously assemble a fully conscious brain, complete with fabricated memories of a past that never existed. And relativity's vast, infinite canvas of spacetime might just make it inevitable. Here's how the horror unfolds. In an eternal universe, even the most improbable events become certainties. Flip a coin enough times and it'll eventually land on its edge. Or in this case, atoms might randomly arrange themselves into a functioning mind. According to relativity, there's no universal clock ticking away the ages. Time stretches and warps, leaving pockets of reality where statistical flukes like this could arise. The kicker, a Boltzmann brain would feel just as real as you do right now, utterly convinced of its own existence, unable to tell it's a cosmic mirage. But why does this matter? Because if relativity's probabilities allow for self-aware illusions to outnumber real observers, our entire understanding of reality crumbles. Every observation, every scientific measurement, even the apparent age and structure of the universe, could be the fabricated memory of a brain that popped into existence 5 minutes ago. It's not just solipsism gone wild, it's a direct challenge to cosmology's foundations. If Boltzmann brains are statistically more likely than stable, evolved beings like us, then the universe we think we know might be nothing more than a fleeting hallucination. Physicists have tried desperately to dodge this paradox. Some argue that the accelerating expansion of space, driven by dark energy, will eventually dilute matter so thoroughly that fluctuations can't assemble even a single brain. Others invoke the anthropic principle. We must be real observers because hypothetical Boltzmann brains wouldn't have consistent experiences to measure anything. But the real shocker is how relativity's own success fuels the problem. Its equations permit universes so vast and ancient that even the absurd becomes unavoidable, leaving us to wonder, is reality a statistical anomaly or the universe's most elaborate glitch? The stakes couldn't be higher. If Boltzmann brains are possible, then science itself, built on observation and repeatable experiments, rests on shaky ground. Why trust the cosmic microwave background or the redshift of galaxies if they might just be phantom data implanted in a transient mind? Some theorists take this as a sign that relativity, while flawless in describing gravity and motion, might need hidden constraints to prevent such absurdities. Others see it as proof that we're missing a deeper layer of physics, one where consciousness and quantum mechanics intertwine in ways we can't yet fathom. For now, the Boltzmann brain remains a specter haunting cosmology, a reminder that even our most elegant theories might be teetering on the edge of unreality. Whether it's a flaw in relativity's probabilities or a clue to something far stranger, one thing's certain: the universe's greatest trick might be convincing us it's even there at all. If black holes are the universe's ultimate one-way streets, where matter vanishes without a trace, then white holes should be their cosmic opposites, gushing fountains of light and energy, spewing out everything a black hole ever swallowed. Einstein's equations allow for these bizarre objects, mathematical mirror images where time runs backward. But here's the catch: while black holes litter the cosmos, white holes remain stubbornly absent. Not a single one has ever been spotted, leaving physicists to wonder, Is relativity teasing us with solutions that don't exist, or are we missing something fundamental about time itself? Picture a black hole's life played in reverse. Instead of collapsing inward, a white hole would explode outward, violently ejecting particles and radiation in a process that looks like a big bang in miniature. Relativity treats time as reversible, so mathematically, white holes are just as valid as black holes. Yet the universe seems to have a glaring asymmetry. Black holes form naturally from dying stars, while white holes, if they exist at all, require conditions so exotic they border on impossible. Some theorists argue this isn't a coincidence. The absence of white holes might be the universe's way of enforcing the arrow of time, a cosmic rule that prevents entropy from running backward. The paradox deepens when you consider quantum mechanics. Black holes evaporate over eons, leaking Hawking radiation until they vanish. But what happens at the very end? Some models suggest a black hole's final moments could trigger a quantum bounce, transforming it into a white hole. It's as if the dying black hole hiccups, spitting back out a fraction of what it consumed. If true, microscopic white holes might be flickering in and out of existence all around us, too fleeting to detect. Others speculate that the Big Bang itself was a white hole event, a primordial eruption of spacetime from a previous universe's collapse. Yet even these speculative ideas run into trouble. White holes violate the second law of thermodynamics, the ironclad rule that disorder always increases. A white hole's outburst would lower entropy locally, like a shattered glass spontaneously reassembling. Relativity permits it, but nature seems to reject it. This tension hints at a deeper truth. Einstein's equations might be agnostic about time's direction, but the universe isn't. The lack of white holes could be a clue that time's flow isn't just an emergent property. It's woven into the fabric of physics at the most fundamental level. So where does that leave relativity? The theory's beauty lies in its symmetry, but reality seems to prefer lopsidedness. Some physicists argue that white holes are mathematical artifacts, solutions that exist on paper but never manifest in nature. Others wonder if we're looking for them wrong. Could dark matter or fast radio bursts be white holes in disguise? Or might they hide in plain sight, masquerading as gamma-ray bursts or other cosmic explosions we've already seen but failed to recognize? The white hole paradox isn't just about missing objects. It's a litmus test for our understanding of time, entropy, and the universe's deepest rules. If white holes truly don't exist, it means relativity's time symmetry is a mathematical quirk, not a physical reality. And if they're out there waiting to be found, they could rewrite everything we thought we knew about causality. Either way, their absence speaks volumes, a silent reminder that the universe has secrets even Einstein couldn't unravel. Einstein's general relativity gave us wormholes, hypothetical tunnels through spacetime, connecting distant regions in an instant. Quantum mechanics, meanwhile, gave us entanglement particles mysteriously linked across vast cosmic distances. For decades, these ideas lived in separate worlds, one ruling the cosmos, the other the subatomic. But what if they're not just connected, but fundamentally the same? That's the audacious claim of the ER equals EPR conjecture, a theory so bold it stitches together relativity and quantum mechanics with a thread Einstein himself might have dismissed as science fiction. The idea is deceptively simple. The refers to Einstein and Rosen's 1935 paper on wormholes, Einstein-Rosen bridges, while EPR nods to Einstein, Podolsky, and Rosen's work on entanglement. At first glance, these concepts couldn't be more different. Wormholes are cosmic shortcuts, bending spacetime so drastically that two distant points touch. Entanglement, on the other hand, defies spacetime entirely. creating correlations between particles faster than light could bridge the gap. Yet in 2013, physicists Leonard Susskind and Juan Maldacena proposed a radical twist. Every pair of entangled particles might be connected by a microscopic wormhole, a hidden tunnel in spacetime's fabric. Picture two electrons born from the same quantum event, sent to opposite ends of the galaxy. Measure one, and its twin instantly mirrors the result, as if they're whispering through a secret passage. The AR equals EPR conjecture suggests that passage isn't metaphorical, it's a real, physical bridge, too tiny and unstable to traverse, but threading through extra dimensions we can't perceive. In this view, entanglement isn't magic, it's geometry. The spooky action Einstein hated becomes the gravitational handshake of a wormhole too small to see. This isn't just poetic symmetry. The math hints at something profound. In string theory, certain entangled states correspond precisely to wormhole solutions in higher dimensional spacetime. It's as if the universe has been hiding its blueprints in plain sight, using quantum entanglement as a cipher for spacetime's hidden architecture. Even Hawking radiation, the slow leak of energy from black holes, might involve microscopic wormholes connecting particles inside and outside the event horizon. But here's where relativity pushes back. Wormholes, as relativity describes them, require exotic matter with negative energy to stay open, a substance we've never observed. Entanglement, meanwhile, needs no such scaffolding. If they're truly the same phenomenon, why does one side of the equation demand impossible ingredients? Skeptics argue this exposes the conjecture's limits, a beautiful idea that hasn't yet bridged the gap between theory and reality. Yet the implications are too tantalizing to ignore. If ER equals EPR, then every entangled pair in the universe is a potential wormhole, weaving spacetime into a vast, invisible network. Quantum computers, which rely on entanglement, might inadvertently be probing this hidden geometry. And the holographic principle, which suggests our 3D universe is a projection of 2D data, gains new weight. Wormholes could be the pixels linking the projection to its source. The conjecture also offers a wild answer to the black hole information paradox. If particles falling into a black hole remain entangled with those outside, their connection via microscopic wormholes could preserve information, preventing it from vanishing forever. It's as if the universe, faced with a cosmic crisis, deployed wormholes as emergency escape routes for data. Whether ER equals EPR holds up or not, it's already reshaped how physicists see the quantum gravity divide. No longer just competing frameworks, relativity and quantum mechanics might be speaking the same language, one where spacetime and entanglement are two dialects of a deeper, unified truth. And if that's the case, then Einstein's greatest unrealized dream, a theory of everything, might be lurking in the quantum threads that stitch the cosmos together. Galaxies should fly apart. That's the unsettling conclusion when you apply Einstein's equations to the cosmos. According to relativity, the visible matter in spiral galaxies, stars, gas, dust, simply doesn't provide enough gravity to keep them spinning as fast as they do. Without some invisible glue holding them together, their outer stars should fling into the void like children tossed from a merry-go-round. Yet here we are, surrounded by pinwheels of light that stubbornly refuse to disintegrate. Scientists call this phantom glue dark matter, an elusive substance that outnumbers ordinary matter 5-1. But here's the twist: after decades of hunting, we've yet to directly detect a single particle of it. This isn't just a gap in our knowledge, it's a crack in relativity's foundation, one that's forced physicists to confront an uncomfortable possibility. What if the problem isn't missing matter, but misunderstood gravity? Enter modified Newtonian dynamics, proposed in the 1980s by physicist Mordechai Milgrom. This radical framework suggests that gravity doesn't weaken as quickly over large distances as Newton or Einstein predicted. Instead, at the faint accelerations found in galaxies' outskirts, it tugs slightly harder, eliminating the need for dark matter altogether. Picture a car that mysteriously speeds up when you ease off the gas. That's how Mund recasts galactic rotation. The math is startlingly elegant. Tweak gravity's behavior below a certain threshold, and galaxies snap into perfect balance without invoking invisible particles. Even more compelling, Mund accurately predicts the rotation curves of hundreds of galaxies using a single adjustable parameter, something dark matter models struggle to match without fine-tuning. Yet relativity isn't surrendering without a fight. While Mund excels at galactic scales, it stumbles when faced with the Bullet Cluster, two colliding galaxy clusters where gravitational lensing reveals mass separated from visible matter. Dark matter glides through the crash unscathed, while Mund requires ad hoc fixes to explain the mismatch. Then there's the cosmic microwave background, whose intricate patterns align precisely with dark matter's fingerprints. Mund proponents argue these aren't fatal blows, but growing pains for a theory still in development. They point to relativistic extensions like TVS tensor vector scalar gravity, which attempt to reconcile Mund with Einstein's framework, bending without breaking it. The stakes couldn't be higher. If dark matter exists, it's a shadow universe waiting to be discovered, a cosmic partner to the world we know. But if Mund is right, it means relativity, while flawless in our solar system, needs a fundamental rewrite on larger scales. Imagine gravity as a language Einstein gave us the dictionary, but Mund hints there's an undiscovered dialect spoken only in the depths of space. Experiments are closing in from both sides. Detectors like LUX Zeppelin hunt for dark matter particles deep underground, while missions like Euclid map the universe's structure in unprecedented detail, searching for deviations from relativity's predictions. Meanwhile, theorists wrestle with quantum gravity's implications. Could dark matter be an artifact of spacetime's granularity? Or does Mund's success point to an undiscovered fluid-like component of the universe? This paradox cuts to the heart of how science confronts the unknown. Do we invent new substances to preserve our theories, or dare to rewrite the theories themselves? For now, the cosmos keeps its secrets, its galaxies spinning silently in the dark, a reminder that even Einstein's towering legacy might be just the first draft of gravity's true story. Empty space isn't empty. That's the unsettling lesson of the Casimir effect, a quantum quirk so strange it makes even the vacuum hum with hidden energy. Picture two metal plates placed microscopically close together in a perfect vacuum. No atoms, no light, nothing but void between them. Common sense says nothing should happen. But quantum mechanics laughs at common sense. In that tiny gap, something extraordinary occurs. The plates snap together as if pulled by an invisible force. This isn't magic. It's the universe's quantum underbelly flexing its muscles, and the implications shake the foundations of relativity itself. The secret lies in what quantum theory calls virtual particles, fleeting pairs of particles and antiparticles that flicker in and out of existence too quickly to detect directly. Normally, they cancel each other out almost instantly, leaving no trace, but squeeze them between two plates and the rules change. Only certain wavelengths of these fluctuations can fit in the narrow gap, while outside, all wavelengths roam free. The result, more virtual particles push on the plates from outside than from inside, creating a net inward force. It's like being in a crowded elevator where everyone's elbows happen to press the doors closed. The Casimir effect proves this isn't just math, it's measurable reality. with lab experiments detecting forces strong enough to move microscopic objects. Here's where relativity sweats. Einstein's equations rely on strict energy conditions, rules about how energy and pressure must behave to keep spacetime stable. Negative energy, which the Casimir effect produces between those plates, violates these conditions. In relativity's world, negative energy shouldn't be able to pile up like this without triggering catastrophic instabilities, wormholes pinching shut, black holes evaporating violently, or worse. Yet quantum mechanics shrugs and serves up negative energy on demand. No cosmic apocalypse required. This isn't just a minor disagreement. It's a glaring mismatch in how the two theories describe the vacuum's very nature. The stakes get even higher when you consider what this means for warp drives and time machines. The Al-Cubier drive, that tantalizing faster-than-light concept, relies on negative energy to bend spacetime into a travel-friendly bubble. The Casimir effect suggests such energy might actually exist, but in amounts too tiny to power a starship. Still, the mere possibility sends theorists scrambling. Could we amplify this effect, harvest it, or does quantum mechanics impose some deeper limit, a cosmic fine print that keeps relativity's nightmares at bay? Some physicists argue the Casimir effect is a red herring, that its negative energy is just a bookkeeping trick, a quirk of reference frames rather than a true violation. Others see it as a clue to a deeper truth, that relativity's energy conditions are approximations like Newton's laws before them, needing a quantum overhaul. Hidden variables, extra dimensions, or even undiscovered fields might bridge the gap, turning this paradox into a Rosetta Stone for quantum gravity. One thing's certain: the quieter the vacuum gets, the louder the universe's secrets become. Those innocuous metal plates aren't just measuring force, they're probing the boundary between two titanic theories, each refusing to yield. And in that fragile gap, where particles blink in and out of existence, we might just find the key to unlocking physics' next great revolution. Imagine firing a photon toward a fork in the road, a beam splitter that could send it left or right. Common sense says the particle must choose one path the moment it hits the split. But quantum mechanics laughs at common sense. In Wheeler's delayed choice experiment, the photon does something downright eerie. It waits to decide whether it took one path or both, not when it reaches the splitter, but later when scientists choose how to measure it. It's as if the photon rewrites its own history retroactively, bending causality like a cosmic choose-your-own-adventure book where the ending changes the beginning. Here's the kicker: this isn't just theory. Labs have run this experiment with photons traveling through interferometers, devices that let particles interfere with themselves, a hallmark of wave-like behavior. If you measure which path the photon took after it's already traveled, it behaves like a particle sticking to one route. But if you erase that path information before measuring, the photon suddenly acts like a wave, having taken both paths simultaneously. The startling implication: the photon's past isn't fixed until the future measurement locks it in. Relativity's rigid light cones, where cause must always precede effect, start to look like shaky scaffolding in the face of quantum whimsy. Einstein's spacetime is built on unbreakable causal order, a universe where events are neatly chained like dominoes in time. Yet Wheeler's experiment suggests quantum systems might play by different rules, where the dominoes wobble until the last second, only settling into place when observed. Some interpretations argue this isn't true time travel, but a quirk of quantum superposition. The photon isn't changing the past, just existing in all possible states until measurement collapses them. Others go further, proposing that time itself might be an emergent property, with quantum events stitching together a semblance of causality only at macroscopic scales. The real tension lies in relativity's insistence on locality. If a photon's decision about its past is truly influenced by a future measurement, does that mean information is somehow looping backward, violating the light speed limit? Or is spacetime's structure more malleable than we thought, with quantum processes threading through hidden folds in reality? Experiments with entangled particles add fuel to the fire. Delayed choice setups using entangled photons show correlations that defy classical notions of time's flow, as if the universe is running on quantum Wi-Fi where cause and effect buffer unpredictably. What's at stake isn't just philosophical. If quantum systems can blur causality, technologies like quantum computers might one day exploit this for unimaginable processing power algorithms where the answer shapes the question. Telescopes could even adapt Wheeler's logic to cosmic scales, using gravitational lensing to choose whether ancient photons from quasars behaved as particles or waves billions of years ago, testing if the universe's quantum rules hold across epochs. For now, the paradox stands as a shimmering mirage on physics' horizon, a hint that time, causality, and even history itself might be far more fluid than relativity's clockwork universe allows. Whether this is a quirk of measurement or a crack in spacetime's foundation, one thing's clear: the photon's delayed choice isn't just rewriting its own past. It's rewriting our understanding of reality. Black holes were supposed to be the universe's ultimate shredders, cosmic trash compactors where matter, energy, and even information vanished forever. Then Jacob Bekenstein and Stephen Hawking dropped a bombshell. Black holes aren't just gravitational monsters. They have temperature, they have entropy. They behave like thermodynamic's strangest furnaces, radiating heat into the void while their interiors remain colder than deep space. This revelation rewrote physics, but it left behind a glaring paradox. If entropy counts the number of ways a system's microscopic parts can be arranged, what exactly are those parts inside a black hole? Relativity paints the event horizon as a smooth, featureless boundary, a perfect mathematical sphere with no hidden structure. So where's the entropy hiding? The answer might lie in the quantum realm's most radical idea, that spacetime itself is pixelated, built from fundamental bits of information. Imagine zooming in on the event horizon until Einstein's smooth geometry dissolves into a frenzied quantum network, like a silk sheet revealing its threads under a microscope. Each thread could be a tiny unit of information, a binary answer to a cosmic yes or no question about what fell into the black hole. Bekenstein's calculations showed that a black hole's entropy is proportional to its surface area, not its volume, a hint that all the information it swallows might be encoded on its two-dimensional boundary, not buried deep inside. It's as if the universe compresses 3D reality into a holographic imprint, like storing an entire library's worth of books on the covers alone. Hawking radiation adds another twist. As black holes slowly evaporate, they release thermal energy that appears to carry no information about what they consumed, a direct violation of quantum mechanics' insistence that information can't be destroyed. But if the event horizon's quantum bits store data like a cosmic hard drive, then Hawking radiation might gradually decode and release that information, pixel by pixel. The problem: relativity's equations break down at this scale, offering no clues about how the translation happens. This isn't just a technical hiccup, it's a screaming mismatch between how gravity and quantum mechanics handle information, with the black hole's fate hanging in the balance. Some theorists argue this paradox points to spacetime's true nature. Just as water's fluidity emerges from the chaotic dance of molecules, gravity and entropy might arise from deeper quantum connections and tangled threads weaving the fabric of reality. The AD-S/CFT correspondence, a landmark idea in string theory, suggests that black holes could be holograms, their three-dimensional gravity a projection of quantum interactions playing out on a distant 2D surface. In this view, the entropy isn't missing, it's just written in a language relativity doesn't yet speak. Experiments are light years away from probing a black hole's event horizon directly, but lab analogs might crack the code. Quantum simulators using ultra-cold atoms or light pulses mimic black hole dynamics, revealing how information could scramble and re-emerge. Meanwhile, gravitational wave detectors listen for subtle echoes in black hole collisions, potential fingerprints of quantum structure at the horizon. Each test is a step toward answering the haunting question: is space-time itself a tapestry of quantum data? And if so, what does that mean for the singularity's infinite depths? The black hole entropy paradox doesn't just challenge theories, it redefines reality's building blocks. If Bekenstein and Hawking were right, then every black hole is a Rosetta Stone, its surface etched with quantum symbols waiting to be read. Decipher them, and we might finally glimpse the universe's hidden code, the one where gravity and quantum mechanics shake hands, and space-time reveals itself as the ultimate illusion. Einstein spent his later years convinced quantum randomness was a sign of incompleteness, that hidden variables lurked beneath the dice rolls of particle behavior, waiting to restore order. But what if the universe had an even more unsettling answer? Enter superdeterminism, a mind-bending twist where the dice were never thrown at all. This radical proposal doesn't just sidestep quantum unpredictability, it erases free will from the equations entirely, suggesting every measurement, every experiment, even every human choice was locked into place at the dawn of time. And in a cosmic irony, this idea resurrected to defend Einstein's skepticism might just dismantle his most cherished principle, local causality. Picture a cosmic puppet show where every particle's motion, every scientist's decision to measure spin up or down, was pre-scripted billions of years ago. Superdeterminism argues that quantum randomness is an illusion, a trick of perspective. When entangled particles seem to choose correlated states instantaneously, they're not communicating faster than light. They're simply following a shared script written before the experiment began. No spooky action, no broken light speed barriers, just a universe running on rails so absolute, even our attempts to test its freedom were predetermined. It's as if the universe conspired to make quantum mechanics look random while hiding a deeper, deterministic machinery beneath. The paradox here is deliciously cruel. Einstein rejected quantum uncertainty because it violated his intuition about a rational, causal cosmos. Yet superdeterminism's fix, a universe so rigidly determined that even experimental setups are pre-correlated, demolishes the very locality he fought to preserve. Relativity's strict, no faster than light signaling rule relies on the assumption that experimenters can freely choose how to measure particles. But if those choices were predetermined alongside the particle states, locality becomes a mirage. The universe isn't respecting light speed limits, it's rigged so violations appear impossible. Critics recoil at the implications. If superdeterminism holds, science itself teeters on shaky ground. How could we trust experiments if our methods, our biases, even our debates about the results were all preordained? It's like a detective realizing every clue, including their own hunches, was planted by the suspect. Some physicists argue this makes superdeterminism untestable by definition, a philosophical dead end. Others, like Nobel laureate Gerard T. Hooft, see it as an unflinchingly honest approach to quantum foundations, however uncomfortable. The real tension lies in the data. Bell's theorem, which proved quantum correlations can't be explained by local hidden variables, assumes measurement settings are chosen independently. Superdeterminism loopholes this by saying the settings and particles share a cosmic ancestry. While no experiment has ruled it out, the sheer fine-tuning required boggles the mind. Every particle interaction since the Big Bang would need flawless coordination to fake quantum randomness today. Yet the idea lingers, a ghost at the feast of physics. If true, it wouldn't just solve quantum mysteries, it would rewrite reality's rulebook, trading relativity's elegant spacetime for a block universe where past, present, and future are equally fixed. Einstein's dream of cosmic order might end up being his theory's undoing, proving the universe is even stranger than quantum mechanics dared suggest. And that's the ultimate paradox. In trying to rescue causality, we might discover it was never there to begin with. Einstein envisioned spacetime as a smooth, unbroken fabric, a cosmic stage where gravity's drama unfolds with geometric precision. But zoom in far enough past atoms, past quarks, past anything we've ever observed, and that elegant fabric might unravel into something far wilder. At the Planck scale, distances so small they make an atom look like a galaxy. The universe could be a seething quantum foam, where spacetime itself churns with violent fluctuations. Imagine an ocean during a storm, but instead of waves, you've got spacetime bubbles popping in and out of existence, twisting reality into knots so tight even relativity's equations go silent. This isn't poetic exaggeration. It's the unsettling prediction of quantum gravity theories, and it hints at a reality Einstein never saw coming. The Planck scale is the universe's ultimate no-go zone, a realm where distances shrink to 10 to the power of negative 35 meters, and time intervals become incomprehensibly brief. Here, gravity's gentle curvature gives way to quantum turbulence, where spacetime's very geometry becomes probabilistic, flickering between countless configurations like static on a cosmic TV screen. Relativity, with its reliance on smooth, continuous fields, has no language for this chaos. It's as if the theory that mastered black holes and the Big Bang hits a wall when confronted with the universe's pixelated fine print. Some physicists argue this isn't a failure, it's a clue. The foaminess might be spacetime's true face, with relativity's smoothness merely an illusion, a low-resolution snapshot of deeper quantum machinery. String theory offers one way out, proposing that spacetime's apparent roughness stems from vibrating strings too tiny to probe directly. Loop quantum gravity takes a different tack, suggesting spacetime is woven from indivisible loops, a fabric with finite threads that can't be split further. Both ideas share a radical premise. Einstein's continuum is an approximation, like mistaking a mosaic for a painting when viewed from afar. The trouble is, testing these ideas directly is nearly impossible. Planck-scale energies dwarf anything our particle colliders can muster. It's like trying to hear a whisper in a hurricane, yet nature might have left breadcrumbs. Some models predict that high-energy cosmic rays, after traveling billions of light-years, could carry subtle scars from spacetime's foamy texture, tiny delays or distortions that betray the turbulence beneath. The real paradox lies in what this means for causality. If spacetime is fundamentally jittery at these scales, then the very notion of before and after could break down. A photon's path might fork unpredictably, as if the universe itself suffers from quantum indecision. Black holes add another layer of weirdness. Their singularities might be Planck-scale firestorms, where relativity's predictions implode into quantum noise. Even the speed of light, relativity's sacred constant, could waver in this froth, its value flickering like a candle in the wind. For now, Planck-scale anomalies remain a theoretical battleground, a frontier where math is our only microscope. But their implications are cosmic. If spacetime isn't smooth, then Einstein's equations are like a grand piano, missing its lowest octave, beautiful but incomplete. Unlocking this quantum cacophony might require a new kind of physics, one where relativity and quantum mechanics aren't just reconciled, but rewritten from the ground up. And when that happens, we might find that the universe's quietest scales are also its loudest, screaming secrets we're only beginning to hear. Black holes are supposed to be the universe's ultimate censors, cosmic editors that ensure the messy drafts of spacetime never see the light of day. According to Einstein's equations, whenever matter collapses into a singularity, an event horizon forms around it like an impenetrable curtain, shielding the outside universe from the infinite chaos within. This elegant rule is known as the cosmic censorship hypothesis. No naked singularities allowed, but recent supercomputer simulations have stumbled onto something scandalous: scenarios where matter collapses so violently or spins so fast that the event horizon never forms. The result, a singularity exposed to the cosmos like an open wound, where the laws of physics dissolve into pure unpredictability. Picture a dying star with just the wrong amount of spin. As it collapses, centrifugal forces fling its outer layers outward while its core implodes, creating a gravitational tug of war. In most cases, gravity wins, wrapping the singularity in an event horizon's protective shroud. But tweak the numbers slightly, a bit more angular momentum, a dash less mass, and the horizon might never materialize. The singularity bursts free, naked and unshielded, its infinite density laid bare for the universe to see. Relativity shudders at the thought. Without an event horizon, the singularity's gravitational fury would propagate outward unchecked, warping spacetime in ways no equation could predict. It's like removing the containment field around a nuclear reactor. The fallout would be catastrophic and uncontrollable. The real mystery is why nature seems to obey this censorship rule so diligently. No confirmed naked singularity has ever been observed despite decades of searching. Some physicists argue this isn't coincidence, that unknown physics steps in to prevent horizonless collapses like a cosmic safety net. Others suspect naked singularities might be hiding in plain sight, masquerading as gamma-ray bursts or other extreme astrophysical events we've misclassified. The simulations permitting them rely on idealized conditions, perfectly symmetrical collapses, frictionless matter, leading skeptics to dismiss them as mathematical quirks rather than physical realities. Yet the implications are too profound to ignore. If naked singularities exist, they'd be more than just cosmic oddities, they'd be portals to a lawless frontier. Predictability, relativity's crown jewel, would crumble near these exposed singularities. Light rays could spiral into infinite loops. Causality itself might tangle into knots. Even more unsettling, some models suggest naked singularities could allow time travel, their infinite curvature twisting world lines into closed time-like curves. Einstein's equations permit these horrors in theory, but the universe seems to veto them in practice. The cosmic censorship hypothesis is more than a tidy rule. It's a lifeline preserving physics' ability to explain the cosmos. If singularities can go naked, general relativity loses its prophetic power, reduced to a proximate theory that fails at the most critical moments. Perhaps that's why nature enforces censorship so strictly, not out of modesty but necessity. Until we find definitive proof of a naked singularity, or prove they're impossible, this paradox remains a stark reminder that even Einstein's masterpiece might have blind spots, places where the universe's rulebook frays at the edges. Einstein's equations describe a universe where time flows forward like an arrow, never looping back on itself except when they don't. In 1949, mathematician Kurt Gödel dropped a bombshell. a solution to relativity's equations where time isn't a straight line but a Möbius strip, twisting into closed loops that let you revisit your own past. Picture a cosmic racetrack where, if you travel far and fast enough, you'd eventually lap yourself, arriving back at the moment you left. Gödel's universe isn't just a thought experiment, it's mathematically flawless, a fully relativistic model where cause and effect tangle into knots. And while our cosmos doesn't seem to work this way, its mere existence in Einstein's framework forces a jaw-dropping question. Did relativity, the theory that banished absolute time, accidentally smuggle time travel into the fine print? Gödel's universe spins not just a little, but violently, like a whirlpool dragging space-time along with it. In this spinning chaos, time becomes a local quirk rather than a universal constant. What's past for one observer could be future for another, with world lines curving back on themselves like Ouroboros snakes eating their own tails. There's no need for wormholes or warp drives here. Just follow the right path at the right speed, and the universe's own geometry would deliver you to yesterday. Einstein was reportedly unsettled by this discovery. His theory, designed to banish paradoxes like Newton's absolute time, had birthed a new one, a universe where history wasn't fixed but rewritable. The real shocker, Gödel's solution obeys every rule of general relativity. Matter curves spacetime, spacetime tells matter how to move, no shortcuts, no cheats. It's as if the universe left a backdoor in its own code, a glitch that turns causality into optional software. Critics argue our universe's expansion and low rotation make Gödel's scenario impossible here, but that misses the point. The paradox isn't about practicality, it's about principle. Relativity, the gold standard of cosmic order, permits timelines so twisted they'd make a time traveler dizzy. This isn't just academic whiplash. If closed time-like curves lurk in relativity's math, even as unrealized possibilities, they demand a reckoning. Quantum mechanics insists information can't vanish, but what happens if a time loop lets a particle interact with its own past, creating feedback that amplifies or erases it entirely? Black hole physics grapples with similar puzzles, suggesting Gödel's ghost might haunt more than just abstract models. Some theorists now speculate that quantum gravity, the long-sought union of relativity and quantum mechanics, could outlaw these loops, patching relativity's paradoxes like a cosmic software update. Yet the allure of Gödel's universe endures. It's a reminder that even our most trusted theories might be stranger than we dare imagine, not just describing reality, but hiding alternate versions of it in their equations. Whether time loops are mathematical mirages or undiscovered features of the cosmos, they force us to confront a humbling truth. Einstein didn't just give us a theory of space-time. He gave us a labyrinth, and we're still mapping the walls. Imagine the universe as a frozen lake on a winter morning, seemingly solid, stable, but secretly balanced on a knife's edge. Beneath its calm surface, quantum physics whispers a terrifying possibility. What if our entire reality is just a fragile layer of ice, and somewhere beneath it lurks a deeper, truer vacuum, one with fundamentally different laws? This is the vacuum decay catastrophe, a scenario so apocalyptic it makes black holes look like playground hiccups. In this nightmare, a single quantum fluctuation could nucleate a bubble of true vacuum that expands at light speed, rewriting physics as it goes. Stars, planets, even space-time itself would unravel mid-collapse, replaced by a new cosmos with alien rules. And here's the kicker: relativity, our trusty guide to gravity and motion, would stand helpless at the sidelines, unable to predict or explain the chaos. The paradox hinges on metastability, a fancy word for temporarily stable. Our universe's vacuum isn't empty, it's simmering with quantum fields that give particles their mass and charge. These fields exist in a local energy minimum, like a marble resting in a shallow dent on a hillside. But what if there's a steeper valley nearby? Quantum tunneling could kick the marble over the edge, triggering a phase transition where the fields reconfigure into a lower energy state. The instant that happens, the bubble's wall races outward, erasing everything in its path. Not with fire or explosions, but something far stranger. The very laws of physics inside the bubble, the strength of gravity, the speed of light, even the nature of matter might be unrecognizable. Relativity's blind spot here is glaring. Einstein's equations describe spacetime's curvature, but they assume the underlying physics is immutable. Vacuum decay doesn't just bend spacetime, it replaces the rulebook governing it. Picture a chess game where the board suddenly morphs, turning pawns into kangaroos and checkmates into limericks. Relativity can't model that transition because it treats constants like the cosmological term as well constant. Yet quantum field theory suggests these constants might be accidents of our metastable vacuum, frozen in place like a supercooled liquid waiting to crystallize. The stakes astronomical. If vacuum decay began somewhere in the cosmos, we'd have zero warning. The bubble's edge would move at light speed, so the first sign of doom would be its arrival. One moment you're sipping coffee, the next your coffee, and the molecules composing it cease to obey familiar chemistry. Some models suggest a new vacuum might be more hospitable, but odds are it wouldn't support atoms, let alone life. The only solace, if it hasn't happened in 13.8 billion years, our vacuum's dent might be deeper than we fear. Yet the paradox lingers. Our best theories can't tell us if this is science or sci-fi. Particle colliders like the LHC hunt for clues by probing extreme energies, hoping to spot but not trigger hints of vacuum instability. Meanwhile, cosmic inflation's echoes in the CMB might hide evidence of past phase transitions, like scars from universes that rewrote themselves long ago. The vacuum decay scenario isn't just a physics puzzle, it's a cosmic game of Russian roulette, with relativity left wondering if the chamber's empty or if the trigger's already been pulled. Neutron stars are cosmic enigmas, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Einstein's general relativity predicts their crushing gravity should compress them into perfect spheres, their interiors a soup of neutrons packed tighter than atoms in a diamond. But the universe loves throwing curveballs. Recent observations reveal neutron stars that defy expectations, some so massive they flirt with the edge of collapse into black holes, others so large their radii stretch relativity's equations to the breaking point. These outliers aren't just oddballs, they're glaring red flags that something fundamental is missing from our understanding of matter under extreme pressure. Take the case of J0740 plus 6620, a neutron star tipping the scales at a staggering 2.14 solar masses. According to relativity, that's dangerously close to the theoretical limit before gravity wins and the star implodes into a black hole. Yet it's not just the mass that puzzles scientists, it's the star's size. Some models suggest such a heavy neutron star should be smaller than Manhattan, squeezed into a tight radius by its own gravity. But measurements from NASA's NICER telescope show it's larger than predicted, as if some unseen force inside is pushing back against collapse like a cosmic spring. This isn't a minor discrepancy, it's a direct challenge to the equation of state, the physics dictating how matter behaves at these unimaginable densities. Here's where relativity hits a wall. The equation of state isn't just about gravity, it's about quantum mechanics, nuclear forces, and possibly exotic particles we've never detected. Under neutron star pressures, protons and electrons might merge into a sea of quarks, or strange matter, a hypothetical form of matter made of strange quarks, could emerge, altering the star's internal structure. Some theories even suggest hyperons, particles heavier than neutrons, could form and soften the star's core, allowing it to grow larger without collapsing. The problem: relativity can't tell us which of these scenarios is correct. Its equations describe gravity's grip, but they fall silent when it comes to the microphysics fighting back. This paradox isn't just academic. Neutron stars are natural laboratories for testing physics beyond Einstein. Gravitational waves from their collisions, detected by observatories like LIGO, carry fingerprints of their internal composition. A heavier or larger star produces a different signal than relativity predicts, hinting at forces stronger than gravity at play. Some researchers speculate these anomalies might point to dark matter lurking in the cores, or even new states of matter that only exist under such extreme conditions. Others wonder if relativity itself needs tweaking at these densities, a gravitational patch to account for quantum effects at macroscopic scales. The stakes couldn't be higher. If neutron stars harbor unknown physics, they could rewrite the rules governing matter itself. Imagine a material so dense it bends spacetime into knots, yet resists collapse with forces we've never seen. It's like discovering a new law of nature written in the heart of a star. Telescopes and gravitational wave detectors are racing to find more of these outliers, each one a potential Rosetta Stone for decoding the universe's most extreme environments. Until then, neutron stars remain a cosmic tug-of-war between relativity's relentless gravity and the mysterious forces daring to push back. When gravitational wave detectors like LIGO first captured the ripples from colliding black holes, it was hailed as relativity's ultimate triumph, proof that spacetime could tremble like a drumhead under cosmic impact. But then came the whispers. Hidden in the data, some researchers claim, are faint echoes lingering after each collision, like sonic aftershocks from a distant earthquake. These aren't part of Einstein's symphony. According to relativity, black holes should ring down cleanly after merging, their gravitational waves fading smoothly like a struck bell. Echoes suggest something far stranger, that event horizons might not be the perfect, featureless membranes relativity describes, but fuzzy quantum structures with hidden textures that bounce spacetime ripples back into the universe. The controversy hinges on the no-hair theorem, one of relativity's most elegant ideas. It states that black holes are bald, devoid of any distinguishing features beyond mass, spin, and charge. Crush a star, a spaceship, or an entire library into a black hole, and all that information vanishes behind the horizon, leaving no trace in the gravitational waves. But quantum mechanics insists information can't truly disappear. The echoes, if real, might be the first clues of a compromised tiny quantum bumps or folds on the horizon that scatter gravitational waves like rocks in a pond, creating interference patterns in the signal. Imagine throwing a pebble into a perfectly still lake and seeing not just concentric rings, but faint secondary ripples returning from some unseen obstacle beneath the surface. That's what proponents argue LIGO might be detecting, evidence that black holes have hair after all, strands of quantum structure peeking through relativity's smooth facade. Skeptics counter that these echoes could be noise glitches in LIGO detectors or artifacts of data processing. The signals are achingly faint, buried deep in the statistical murk where wishful thinking can masquerade as discovery. But the theoretical stakes are too high to ignore. If horizons aren't perfectly smooth, it could mean black holes are surrounded by fiery quantum fuzz, a turbulent zone where spacetime itself becomes granular. Some models even suggest echoes might come from wormholes, exotic tunnels connecting black holes to other regions of spacetime, or from remnants of collapsed objects that stop short of forming true singularities. Each possibility paints a radically different picture of what happens when matter crosses the point of no return. What makes this paradox so explosive is the way it forces relativity and quantum mechanics to confront each other in the wild, not just on paper. Gravitational wave astronomy is still in its infancy, and future detectors like the space-based LISA Observatory could settle the debate by capturing cleaner signals. For now, the echoes remain a tantalizing maybe, a hint that black holes might be cosmic Rosetta Stones, their surfaces etched with quantum graffiti waiting to be decoded. Whether they're real or mirages, one thing's clear: Einstein's pristine black holes are starting to look a little messy. Galaxies racing away from us at the universe's edge aren't just following Hubble's law, they're breaking it. The farther we peer into the cosmos, the more these distant starlight islands seem to move with a mind of their own, their velocities defying the smooth, uniform expansion Einstein's equations predict. Some spiral away faster than expected, as if shoved by an unseen hand, while others lag behind like cosmic stragglers. This isn't just random noise, it's a systematic anomaly, one that suggests space-time might not stretch evenly in all directions. Imagine inflating a balloon covered in dots, only to watch certain patches bulge unpredictably while others barely expand at all. That's the puzzle astronomers face today, and it's shaking the foundations of modern cosmology. The Hubble-Lemaitre law, the bedrock of our expanding universe model, states that a galaxy's recession speed should be perfectly proportional to its distance, a clean, linear relationship driven by dark energy's relentless push. Yet when scientists map thousands of galaxies at the observable universe's fringes, the data scatters wildly. Some regions appear to stretch faster, others slower, as if the cosmos has developed gravitational hotspots and cold spots invisible to our telescopes. One leading explanation, inhomogeneous cosmology, the idea that matter isn't distributed as evenly as relativity assumes. If vast superclusters or cosmic voids warp spacetime on scales larger than we've measured, they could tweak local expansion rates like currents in a cosmic ocean. But there's a more radical possibility. What if dark energy itself isn't constant? Relativity treats it as a uniform force woven seamlessly into spacetime's fabric. Yet if this energy fluctuates stronger in some regions, weaker in others, it could explain the uneven expansion without invoking unseen matter. Think of dark energy as wind buffeting a sailboat. Steady breezes create smooth motion, but erratic gusts leave the vessel lurching unpredictably. Some theorists even speculate these variations could hint at extra dimensions, where dark energy leaks unevenly into our universe from higher dimensional space. The stakes go beyond theory. If expansion isn't uniform, it could force a recalibration of the universe's age, size, and ultimate fate. Measurements of the Hubble constant, the rate of cosmic expansion, already disagree by unsettling margins depending on whether we use nearby supernova or the cosmic microwave background. An inhomogeneous cosmos might resolve this Hubble tension by revealing we've been averaging out cosmic wrinkles that were never meant to be smooth. Upcoming telescopes like the Vera Rubin Observatory will map billions of galaxies, hunting for patterns in the chaos. What they find could either patch relativity's equations or unravel them entirely, revealing a universe far lumpier and far stranger than Einstein ever imagined. At the edge of a black hole's event horizon lies one of relativity's most surreal arenas, the photon sphere. This invisible boundary where gravity bends spacetime so severely that light itself orbits in perfect loops becomes a cosmic hall of mirrors. Imagine a beam of light circling the black hole like a car on a racetrack, neither falling in nor escaping, trapped in an endless celestial waltz. According to Einstein's equations, time for these photons should stretch to a near standstill. An observer watching from afar would see their light redshifted into oblivion, each orbit stretched across eons, while from the photon's perspective, if it had one, the trip would feel instantaneous. But here's the twist: quantum mechanics insists photons don't experience time at all. They're born, they travel, they're absorbed, all without a single tick of an internal clock. This isn't just a philosophical quirk, it's a full-blown showdown between relativity's time-bending gravity and quantum mechanics' timeless particles. Dive into the quantum realm and photons become even stranger. In experiments where single photons are split and sent along different paths, their behavior suggests they don't age or decay like particles with mass. A photon emitted from a star a billion light-years away arrives at your eye exactly as fresh as one created in a lab nanosecond ago. Quantum field theory treats photons as excitations in an eternal, unchanging field, more like vibrations in a cosmic guitar string than objects moving through time. This clashes violently with relativity's portrayal of photons trapped in the photon sphere, where their orbits are subject to extreme gravitational time dilation. If time slows to a crawl near a black hole, how can a photon, which supposedly doesn't experience time, be affected? The paradox sharpens when you consider entanglement. Photons linked in quantum pairs seem to communicate instantly across vast distances, as if spacetime's rules don't apply to them. Yet toss one of those entangled photons into a black hole's photon sphere, and relativity insists its orbital period would stretch infinitely from an outsider's view. Does that mean its entangled partner, light years away, would somehow feel this time distortion? Or does quantum mechanics override gravity's grip, leaving the photon's timeless nature untouched? Some theorists argue this tension hints at a deeper truth, that time itself might be an emergent property, a collective illusion born from quantum interactions, rather than the fundamental backdrop relativity assumes. Black holes aren't the only place this duel plays out. Lab experiments with slow light, photons dragged to near standstill in ultra-cold gases, show that while their group velocity plummets, their quantum phase remains unchanged. It's as if the photon's internal experience ignores the slowdown entirely. If that's the case, why would a black hole's gravity be any different? Unless, of course, relativity and quantum mechanics are describing two sides of the same coin, with the photon sphere acting as a cosmic crucible where their differences melt away. The implications ripple far beyond theoretical puzzles. If photons truly are timeless, it could reshape how we interpret the universe's most distant objects. Quasars flickering at the edge of the observable universe might not be subject to the same time dilation we assume, skewing measurements of cosmic expansion. Even our understanding of black hole evaporation through Hawking radiation, a process reliant on photon-like virtual particles, might need revisiting. The photon sphere paradox isn't just about light trapped in orbit. It's about whether time itself is an illusion, a tool, or a tapestry we've only begun to unravel. And at the heart of it all, a single question lingers. When light dances on the edge of eternity, who's keeping time? The cosmos hummed a lullaby in its infancy, deep, resonant vibrations rippling through the primordial plasma like sound waves echoing through a cosmic canyon. These are the Sakharov oscillations, named after physicist Andrei Sakharov, who first predicted their existence in 1965. Today, we detect their fingerprints in the cosmic microwave background, the afterglow of the Big Bang, as faint temperature variations, a billion-year-old echo of the universe's first notes. But here's the cosmic hiccup. These oscillations don't quite match the symphony relativity's inflation theory composed. According to Einstein's framework, the early universe should have expanded exponentially in a split second, smoothing out irregularities like a baker kneading dough. Yet the Sakharov patterns suggest a messier birth, with oscillations that align more closely with alternative models like bouncing cosmologies or variable speed inflation. It's as if we've found scratches on a vinyl record everyone swore was pristine, hints that the universe's opening act might need a rewrite. Dive into the data, and the discrepancies grow louder. Inflation predicts a specific spectrum of oscillations, a harmonic series where larger waves correlate neatly with smaller ones. But the Planck satellite's meticulous maps of the cosmic microwave background reveal anomalies. Certain overtones are muted, while others ring too loud, like a piano with stuck keys. Some theorists argue this could mean inflation wasn't the smooth, relentless process we thought. Instead, the early universe might have pulsed unevenly, with expansion rates that stuttered or surged. Imagine blowing up a balloon in fits and starts, some stretches smooth, others wrinkled. If true, this challenges relativity's assumption that gravity and space-time behaved uniformly in those first moments. The plot thickens when you consider bouncing cosmology, a radical alternative where the Big Bang wasn't a true beginning but a rebound from a previous universe's collapse. In this scenario, Sakharov oscillations wouldn't be primordial echoes but inherited vibrations, like ripples from a stone tossed into a pond before time began. The math reveals something startling. Certain oscillation patterns in the cosmic microwave background align more cleanly with a bounce than with inflation's predictions. Relativity, of course, permits such models. Einstein's equations famously allow for cyclical universes, but they demand exotic physics, like quantum gravity effects that soften the bounce into something smoother than a singularity. What's truly at stake here isn't just a tweak to cosmic history. Inflation ties directly to relativity's vision of spacetime as a dynamic, stretchable fabric. If the Sakharov anomalies force us to abandon or modify inflation, it could mean spacetime itself behaved differently in the universe's first moments, perhaps governed by quantum rules that blurred the very notion of distance and duration. Future telescopes, like the Simons Observatory, will scrutinize these oscillations with unprecedented precision, hunting for telltale signs of whether inflation's flaws are mere wrinkles or full-blown fractures in our cosmological model. The Sakharov oscillations aren't just relics of a bygone era. They're a tuning fork still vibrating, testing whether Einstein's universe sings in perfect harmony, or whether, hidden in its deepest notes, there's a discord waiting to unravel everything we thought we knew. String theory promises to be the grand unified theory. Einstein dreamed of a framework where quantum mechanics and gravity finally shake hands. But lurking in its mathematical garden is a patch of forbidden ground, the swampland. These aren't literal marshes, but universes that string theory declares off limits, no matter how perfectly they obey Einstein's equations. Imagine crafting a beautiful clockwork universe where relativity's rules hold flawlessly, only to be told by quantum gravity that your creation is cosmic fiction, a mirage that can't exist in reality. That's the swampland conjecture in a nutshell, a stark warning that even our most elegant relativistic models might be missing invisible fences, boundaries the universe itself refuses to cross. Take dark energy, the mysterious force accelerating cosmic expansion. Relativity allows it to be a constant, unchanging over time, a cosmological constant Einstein once called his greatest blunder. But swampland conjectures suggest a shocking twist. Dark energy can't be truly constant. It must decay, fluctuate, or interact with other fields, or else the universe becomes too stable to support the quantum structures string theory demands. It's as if the cosmos has a built-in expiration date, a timer counting down to some inevitable shift. This isn't just philosophical nitpicking. Telescopes like Euclid are already hunting for signs of evolving dark energy, testing whether our universe sits on solid ground or teeters on the edge of the swampland. The stakes get even higher when you consider the fate of black holes. Relativity permits extremal black holes, ones with the maximum possible charge or spin, that hover just shy of breaking the cosmic speed limit. Yet swampland rules insist these objects can't exist in nature. Their flawless symmetry would violate quantum gravity's need for messiness, a requirement called the weak gravity conjecture. This principle argues that gravity must always be the weakest force in any viable universe, preventing black holes from becoming too perfectly charged or spinning too fast. It's like the universe has a safety valve, ensuring that no object becomes so extreme it shatters the quantum scaffolding holding reality together. What's fascinating is how these conjectures flip the script on relativity's successes. Einstein's equations describe a universe of breathtaking mathematical beauty, but the swampland hints that this beauty might be too perfect, an idealized sketch that ignores quantum gravity's gritty details. Picture a painter who only works in bold, primary colors, missing the subtle shades that make a scene feel real. The swampland isn't dismissing relativity. It's arguing that the theory's most exotic solutions might be mirages, mathematical ghosts that vanish when quantum gravity turns on the lights. Critics argue this is string theory's way of moving the goalposts, declaring incompatible universes unphysical, rather than admitting the theory's limitations. But supporters counter that the swampland could be a Rosetta Stone, revealing hidden quantum constraints that future theories must obey. Whether it's a roadmap or a reckoning, one thing's clear: Einstein's universe might be just one island in a vast archipelago of possibilities, with the swampland guarding the shores of what's truly possible. And that forces us to ask, if relativity describes worlds that can't exist, what else might we be missing? Einstein's equations flirt with a tantalizing possibility: wormholes, those cosmic shortcuts bending space-time like a folded piece of paper, could be more than just science fiction. The Ellis wormhole, a hypothetical tunnel through the universe's fabric, emerges as a mathematically valid solution to relativity, a gleaming bridge between two distant points in space. But here's the cosmic catch. To stay open, these wormholes demand a substance so bizarre it defies the known laws of physics: exotic matter. Not just any matter, but stuff with negative energy density, capable of repelling gravity itself, propping the wormhole's throat open against the crushing weight of spacetime's natural curvature. It's like trying to build a tunnel through a mountain, only to realize the walls require a material that actively pushes outward instead of collapsing inward. Quantum mechanics, however, isn't playing along. The quantum energy conditions, a set of rules governing how matter and energy behave at microscopic scales, forbid the existence of stable exotic matter in large quantities. Sure, quantum fields permit fleeting bursts of negative energy, like virtual particles borrowing energy from the vacuum before vanishing, but sustaining enough to stabilize a wormhole. That's like trying to power a city with firecrackers. The Casimir effect, where metal plates in a vacuum experience a whisper of negative energy, proves the phenomenon exists, but scaling it up to cosmic proportions would require violating quantum inequalities, the very laws that keep the vacuum from imploding into chaos. This leaves wormholes in a paradoxical purgatory. Relativity winks at their possibility, sketching blueprints for structures that quantum mechanics immediately tears up. The Ellis wormhole isn't just unstable, it's caught in a tug of war between two titanic theories, each pulling reality in opposite directions. some theorists refuse to surrender, proposing workarounds like quantum loopholes, where exotic matter might be concentrated in ultra-thin shells or shielded by undiscovered fields. Others speculate that dark energy, the enigmatic force accelerating the universe's expansion, might share properties with the exotic matter wormholes crave. But these are Hail Mary passes into uncharted physics, gambles that the universe hides a deck of cards we've yet to shuffle. The stakes couldn't be higher. If traversable wormholes are possible, even in principle, they'd rewrite the rules of causality. A wormhole could link not just spaces but times, turning time travel into an engineering problem. Yet quantum mechanics, with its ironclad no-go theorems, stands like a bouncer at the door of the cosmos, arms crossed. The Ellis wormhole's fate hinges on a deeper question. Is space-time's fabric more malleable than we've dared imagine? Or are these cosmic shortcuts just mirages in the desert of Einstein's equations, beautiful but forever out of reach? Until we crack quantum gravity's code, wormholes remain the universe's ultimate tease, a promise written in equations that reality might never let us cash. At near light speeds, time doesn't just slow down, it collapses into a surreal slideshow of cosmic history. Einstein's relativity predicts that as you accelerate toward the speed of light, the universe around you would appear to fast forward, stars flaring and dying in the blink of an eye, galaxies spinning like tops until the entire history of the cosmos plays out in what feels like seconds. To the traveler, it's as if time itself has hit the brakes everywhere but inside their ship. But here's where quantum mechanics throws a wrench into this relativistic dreamscape. At the smallest scales, time never truly freezes. Quantum processes like the decay of particles or the flickering of virtual pairs continue ticking even at near light speeds, as if the universe refuses to let time grind to a complete halt. This creates a bizarre perceptual rift, a universe where relativity says time should stop, but quantum mechanics insists it's always humming along. Think of it like watching a movie on fast forward while the projector's inner gears keep turning at normal speed. Relativity gives you the illusion of a universe sprinting toward its conclusion, but quantum mechanics reveals the clockwork behind the scenes, where time's gears never stop moving. Experiments with high-speed particles like those in CERN accelerators catch glimpses of this paradox. Muons, unstable particles that decay in microseconds, live longer when racing near light speed, a classic demonstration of time dilation. But their decay clocks never fully stop, they just stretch as if time becomes elastic without ever snapping. Quantum fields, too, continue their ceaseless fluctuations, proving that even at velocities where relativity suggests time should stand still, the microscopic world remains stubbornly active. This rift isn't just a quirk, it's a clue that time might be more layered than relativity accounts for. Einstein's theory treats time as a smooth, pliable dimension, but quantum mechanics hints at something grainier, like a film reel with frames too small to see. Some theorists speculate that time's flow could be an emergent property, a collective illusion created by quantum events piling up like sand in an hourglass. If true, then the relativistic time stop isn't a true freeze, just a macroscopic illusion masking quantum ticks we're not yet equipped to measure. Others propose that time dilation's limits are baked into the fabric of spacetime itself, a failsafe preventing the universe from ever fully pausing, lest quantum coherence and reality itself unravel. The implications ripple far beyond thought experiments. If time can't truly stop, even at light speed, it reshapes how we think about black holes, the Big Bang, and the far future of the cosmos. Could an astronaut falling into a black hole perceive infinite time dilation? Or would quantum effects keep their experience finite? And if the universe's expansion eventually isolates galaxies beyond light's reach, Will quantum timekeeping persist in those lonely voids, or will relativity's frozen wastelands take over? The answer might lie in a deeper theory, one that stitches together relativity's cosmic clock with quantum mechanics' relentless ticks, a theory where time isn't just stretched or slowed, but fundamentally rewritten. For now, the paradox stands as a reminder that even at the edge of light speed, the universe guards its secrets fiercely. Time might bend, twist, and crawl, but it never truly stops, because somewhere in the quantum undercurrents, the universe is always ticking. What if gravity isn't a force at all, but something far stranger, a cosmic illusion conjured by the universe's hidden chaos? That's the radical proposition of Eric Verland's emergent gravity, a theory that flips Einstein's spacetime on its head. Instead of matter curving spacetime like a bowling ball on a trampoline, Verland suggests gravity emerges from something far more abstract, the way information organizes itself across the cosmos. Picture a crowd at a concert, individuals jostling randomly, but collectively creating waves that ripple outward. In this view, gravity isn't a fundamental force. It's the statistical outcome of countless microscopic interactions we've never noticed, like thermodynamics revealing how heat arises from atoms in motion. The key lies in entropy, a measure of disorder but also of hidden possibilities. Verland's math shows that when entropy changes across space, say near a massive object like a galaxy, it creates what looks like a gravitational pull. Imagine standing in a room where one side is packed with people and the other is empty. The natural tendency to spread out creates pressure, almost as if an invisible hand were pushing. Emergent gravity argues that space-time itself is this crowded room, with entropy gradients driving what we perceive as gravity, the stunning implication. Einstein's geometric masterpiece, general relativity, might just be the tip of a far deeper iceberg, a macroscopic approximation of quantum information theory playing out on scales we're only beginning to fathom. What makes this paradox so explosive is how neatly it handles dark matter, the elusive substance thought to outweigh visible matter 5-to-1. Astronomers infer dark matter's existence from the way galaxies rotate faster than relativity predicts, as if hidden mass is tugging on stars. But Verland's framework reproduces these rotation curves without invoking dark matter at all. Instead, the extra pull comes from entropy's hidden structure, like a magician's trick where the real action happens offstage. It's as if we've spent decades searching for invisible ink, only to realize the message was written in lemon juice all along, visible once held to the right theoretical light. Critics pounce on the gaps. Emergent gravity struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate their visible and invisible mass like oil and water. Yet supporters counter that relativity had its own growing pains. Einstein's equations initially couldn't account for Mercury's wobbly orbit until subtle corrections were made. The real test may come from quantum labs, where experiments with ultra-cold atoms and holographic principles are probing whether entropy can indeed mimic gravity's effects. If verified, it would mean space-time isn't the smooth continuum Einstein envisioned, but a tapestry woven from information's invisible threads, a universe where gravity isn't the director of the cosmic play, but an actor following a script written in quantum bits. The stakes couldn't be higher. If Verland is right, we're not just tweaking gravity, we're redefining reality's building blocks. Black holes might not be spacetime's dead ends, but information processors, their event horizons bustling with quantum computations. The Big Bang could shift from a singular explosion to a phase transition in entropy, like steam condensing into water. Even time itself might emerge from this chaos, a byproduct of the universe's relentless drive toward disorder. For now, the paradox lingers. Is gravity the universe's architect or just its janitor, sweeping up the mess left by deeper, unseen laws? The answer could rewrite physics, not with a new equation, but by revealing that the oldest force we know is nothing more than a cosmic mirage. The first ever image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, should have been a pristine confirmation of Einstein's predictions, a perfect dark circle framed by a fiery ring of light like a cosmic bullseye. Instead, it revealed a lopsided glow, brighter on one side than the other, as if someone had tilted the universe's flashlight. While general relativity explains the asymmetry as a Doppler effect from the black hole's spin, the unevenness is more extreme than expected, hinting at something deeper. Could this be the first visible crack in relativity's flawless facade? A sign that quantum turbulence near the event horizon is warping spacetime in ways Einstein never imagined. Dive into the numbers and the anomaly gets stranger. The brightness disparity in M87's black hole, the one immortalized in that groundbreaking image, doesn't quite match simulations based solely on relativity. The fiery ring's southern edge blazes noticeably brighter than the north, a skew that persists even after accounting for the black hole's rotation. Some theorists argue this mismatch points to quantum effects churning beneath the surface. Picture the event horizon not as a smooth mathematical boundary, but as a frothing sea of virtual particles popping in and out of existence, their collective energy distorting the surrounding spacetime like heat ripples over a desert highway. These quantum fluctuations could subtly alter how light escapes the black hole's grip, creating hotspots in the accretion disk that relativity alone can't explain. The real bombshell, this asymmetry might be a direct window into quantum gravity. String theory predicts that black holes could be fuzzballs, dense tangles of vibrating strings whose surfaces bristle with quantum chaos. In such a scenario, the event horizon wouldn't be the featureless membrane relativity describes, but a textured landscape where extra dimensions or quantum fields create microscopic hills and valleys. Light skimming this terrain would scatter unevenly, much like sunlight glinting off a stormy ocean, producing the lopsided glow we observe. Alternatively, loop quantum gravity suggests spacetime itself might be pixelated at the tiniest scales, with the black hole's shadow bearing the faint jaggies of this underlying granularity. What's thrilling is that future telescope arrays, like the next-generation Event Horizon Telescope with space-based components, could resolve these anomalies in razor-sharp detail. If the brightness variations follow distinct patterns, perhaps spirals or fractal-like structures, it could betray the fingerprints of quantum geometry. Even more tantalizing, if the asymmetry fluctuates over time, it might reveal the event horizon's quantum turbulence in real time, like watching smoke curl from an extinguished candle. For now, the shadow's lopsided glow remains a cosmic Rorschach test, open to interpretation. It could be a quirk of plasma dynamics in the accretion disk, or it might be the first observational clue that black holes are weirder and far more quantum than relativity ever allowed. One thing's certain, Einstein's pristine black holes are starting to look a little messy, their perfect symmetry ruffled by the universe's hidden quantum undercurrents. And that's exactly where the next revolution in physics might be hiding. Superconductors are supposed to follow the rules, electrons pairing up and gliding through materials without resistance, but only under frigid conditions approaching absolute zero. That's what classic physics predicted, until scientists stumbled upon high-temperature superconductors that defy the playbook, working at temperatures relativity insists should shatter their delicate quantum bonds. These materials don't just bend the rules, they seem to rewrite them entirely, conducting electricity with zero resistance at temperatures warm enough to make liquid nitrogen seem balmy. The puzzle, according to Einstein's framework, the thermal chaos at these higher temperatures should obliterate the fragile electron partnerships that make superconductivity possible. Yet here they are, humming along as if relativity's speed limits and energy barriers don't apply. Dig deeper, and the paradox only gets stranger. In conventional superconductors, electrons form Cooper pairs, duos bound together by vibrations in the material's atomic lattice, like two dancers tethered by a shared rhythm. Relativity sets strict limits on how far these pairs can stretch before thermal energy tears them apart, which is why traditional superconductors only work near absolute zero. But high-temperature variants like copper-based cuprates or iron-based superconductors thrive in conditions that should be electron-pairing graveyards. It's as if these materials have discovered a secret handshake, a way to sustain quantum harmony even as the atomic world around them erupts in thermal noise. Some theorists suggest the answer lies in quantum glue, an exotic form of cohesion that transcends the usual lattice vibrations, perhaps mediated by spin fluctuations or hidden electronic symmetries. Others wonder if relativity's grip weakens in these materials, with electrons exploiting quantum entanglement to maintain their partnerships across longer distances than classical physics allows. The implications are electrifying, literally. If we could decode how these superconductors sidestep relativity's constraints, it might unlock room temperature superconductivity, revolutionizing everything from power grids to quantum computers. But the real mystery is what this means for Einstein's legacy. Are these materials merely outliers, their behavior explainable with tweaks to existing theory? Or do they point to a deeper layer of physics where quantum entanglement or higher dimensional interactions create cohesion that relativity can't describe? Experiments with ultra-fast lasers and quantum simulations are now probing these materials' secrets, hunting for clues in the way light interacts with their electrons. What they find could redefine not just superconductivity, but our understanding of how quantum mechanics and relativity collide or collapse under extreme conditions. One thing's certain, high-temperature superconductors aren't just engineering marvels. They're cosmic riddles whispering that the universe's rulebook might have chapters even Einstein couldn't read. And somewhere in their atomic lattices, the next revolution in physics could be waiting, charged and ready to break through. The cosmic microwave background is often called the universe's baby picture, a snapshot of its infancy, frozen in time and stretched across the sky. But in this ancient light, astronomers have found a blemish so strange it defies everything we thought we knew about cosmic evolution. Stretching over 1.8 billion light-years near the constellation Eridanus lies the CMB cold spot, a region of space inexplicably colder than its surroundings by about 70 microkelvin. That might sound trivial, but in the ultra-precise world of cosmology, it's like finding a snowball in a desert. According to relativity and standard inflationary models, such a massive temperature dip shouldn't exist. The universe's early expansion should have smoothed out any irregularities this extreme, leaving the CMB as uniform as freshly poured cream. Yet there it is, a cosmic bruise that refuses to fade. One explanation flirts with science fiction. The cold spot could be evidence of a collision with another universe. In the multiverse scenario, where countless bubble universes inflate eternally, our cosmos might have bumped into a neighbor during its infancy. The energy from that impact could have drained away photons in the collision zone, leaving behind a chill that persists billions of years later. It's like pressing an ice cube against warm glass. The spot cools where contact occurred. But relativity bristles at this idea. Inflationary models assume universes expand in isolation, their boundaries forever out of reach. If the cold spot is a crash site, it would mean the multiverse isn't just theoretical, it's close enough to leave skid marks on our sky. Then there's the cosmic defect theory. Imagine the early universe as a cooling vat of molten metal. As it solidifies, cracks or imperfections might form in space-time structure. Cosmic strings or textures left over from phase transitions in the primordial soup. These defects could warp the space around them, creating vast voids where matter is sparser and light loses energy as it travels through, appearing colder to us. The cold spot aligns suspiciously with a giant supervoid, a region where galaxies are oddly scarce. But here's the catch: relativity says voids this large shouldn't exist either. The cold spot supervoid is so enormous that standard cosmology struggles to explain how it could form naturally, like finding a mile-wide bubble in a perfectly stirred cup of coffee. What makes this paradox so tantalizing is that both explanations, colliding universes and cosmic defects, require rewriting relativity's playbook. Inflation, the dominant theory of the universe's exponential early expansion, has no room for anomalies this extreme. If the cold spot is a defect, it suggests inflation wasn't as smooth as we thought. If it's a multiverse fingerprint, it hints at physics beyond Einstein's framework, where universes interact in ways his equations never anticipated. Future telescopes like the Simons Observatory aim to study the cold spot's polarization patterns, hunting for clues in the way its light twists. The answer could reveal whether this anomaly is a flaw in our models, or a window into a reality far stranger than relativity ever imagined. For now, the cold spot remains a cosmic Rorschach test. Some see it as a statistical fluke, a random fluctuation magnified by our human tendency to find patterns. Others view it as a crack in cosmology's foundation, proof that the universe's first moments were messier, wilder, and more interconnected than we've dared to suppose. Either way, it's a reminder that even the oldest light in the sky still holds secrets, and that Einstein's universe might be just one page in a much weirder story. Protons are the universe's ultimate survivors, tiny, unshakable anchors of matter that outlast stars, planets, even black holes, or at least that's what relativity assumes. According to Einstein's framework, these subatomic particles should be as eternal as spacetime itself, their stability woven into the fabric of the cosmos. But grand unified theories, those ambitious blueprints aiming to merge all fundamental forces, tell a different story. They predict protons should decay, crumbling into lighter particles over unfathomably long timescales. The catch: relativity's equations have no room for such quantum instability, treating protons as immutable building blocks. This isn't just a minor disagreement, it's a seismic clash between quantum mechanics' restless, probabilistic world and relativity's steadfast, geometric universe. Picture a sandcastle on a beach, its grains fixed in place by perfect, unbreakable bonds. That's how relativity sees protons, timeless, unchanging. But duties whisper that even the sturdiest castles eventually erode. In these models, protons aren't permanent. Given enough time, around 10 to the power of 34 years, quantum fluctuations could spontaneously transform a proton into a positron and a pion, a process as quiet as it is revolutionary. The math is elegant, but the implications are explosive. If protons decay, relativity's assumption of immutable matter crumbles, forcing us to rewrite how space-time interacts with quantum particles at the most fundamental level. The hunt for proton decay is already underway, hidden in labs buried deep underground to shield from cosmic noise. Experiments like Super Kamiok and in Japan monitor colossal tanks of ultra-pure water, waiting for a single proton to vanish in a flash of telltale light. Decades of watching have yielded nothing. Protons stubbornly refuse to decay, living at least 10,000 times longer than GOTs predict. This leaves physicists at a crossroads. Are the theories wrong, or are we simply too impatient? Some propose tweaks to GOTs, adding new symmetries or particles to stretch proton lifetimes. Others wonder if relativity needs a quantum update, introducing subtle spacetime tremors that could nudge protons toward decay. The stakes couldn't be higher. Detecting proton decay wouldn't just validate grand unified theories, it would expose a hidden fragility in matter itself, revealing that even the protons in your body carry an expiration date. Worse, it would force relativity to confront a universe where spacetime's stability is an illusion, where the very bedrock of atoms is subject to quantum whim. Imagine a world where the stars above you, the ground beneath you, even the air you breathe are all slowly, invisibly unraveling. It's a haunting thought, one that blurs the line between physics and philosophy. Yet the absence of decay is just as puzzling. If protons truly are eternal, then GOTs might need a radical rethink, or perhaps relativity's grip on the quantum world is tighter than we thought. Either way, the proton lifetime paradox isn't just about particle physics. It's a tug of war between two visions of reality, one where matter is fleeting and another where it's everlasting. And until a proton finally cracks or definitively doesn't, the universe keeps its secrets close, leaving us to wonder, is everything around us built to last, or are we all just borrowing time? Quantum systems are notoriously fragile. Expose them to the slightest disturbance, and their delicate superposition collapses into definite states, a process called decoherence. But here's where relativity throws a wrench into the quantum world. According to Einstein's time dilation, a quantum particle moving at near light speed should experience time slower than its stationary counterparts. This means its internal clock ticks at a different rate, which ought to slow its decoherence from our perspective. Yet experiments reveal something far stranger. Quantum systems sometimes decohere faster when in motion, as if the universe can't decide whether relativity should protect or disrupt quantum weirdness. Take a hypothetical quantum bit, a qubit, zooming through space at a fraction of light speed. From our lab's perspective, time for the qubit is stretched, so its quantum oscillations should appear sluggish, like a dancer moving in slow motion. That slower ticking ought to delay decoherence, giving the qubit more time to maintain its superposition. But when physicists tested this by sending entangled particles on high-speed journeys like in satellite-based quantum experiments, the results defied expectations. Some particles held their quantum states longer, as relativity predicted, while others collapsed prematurely, almost as if motion itself introduced new sources of interference. It's like shaking a snow globe and expecting the flakes to fall slower, only to watch them swirl into chaos faster instead. The ambiguity cuts to the heart of a deeper conflict. Relativity treats spacetime as a smooth stage, while quantum mechanics insists the stage itself is made of jittery, uncertain pixels. When the two theories collide over something as fundamental as time, the contradictions ripple outward. One camp argues that relativistic motion exposes quantum systems to unseen environmental noise, virtual particles in the vacuum, for instance, which might interact more intensely with a fast-moving object. Others speculate that acceleration, not just velocity, could be the culprit, jostling quantum superpositions apart like a bumpy car ride scrambling a house of cards. The most tantalizing possibility, this paradox might hint at a hidden layer of physics where relativity and quantum mechanics negotiate their differences. Just as GPS satellites must account for both gravitational time dilation and quantum clock precision, Perhaps quantum decoherence operates on rules that blend the two theories in ways we haven't yet formalized. Future experiments with ultra-fast particle accelerators or quantum probes in space could force the issue, revealing whether this tension is a bug or a feature of a deeper, unified reality. Until then, the universe seems content to keep us guessing, letting quantum particles dance just out of step with relativity's metronome. Galaxies should slow down at the edges, like a merry-go-round where the outer horses creep along while the inner ones whip around. That's what relativity predicts when you calculate the gravitational pull of a galaxy's visible stars, gas, and dust. But the universe loves a good plot twist. Astronomers measuring spiral galaxies in the 1970s found something bizarre. Stars in the outer arms were racing just as fast as those near the core, as if some invisible hand kept them from flying off into the void. Dark matter became the go-to explanation, a mysterious, unseen substance whose gravity shores up these whirling cosmic pinwheels. Yet even with dark matter factored in, some galaxies spin too fast, their outer stars defying both Newtonian physics and Einstein's refined equations. It's as if the universe left us with a half-solved equation, daring us to find the missing variables. Take the ultra-diffuse galaxy NGC 1052DF2, a wispy, ghostly structure with almost no dark matter. By all rights, its stars should be sluggish, dragging through space without dark matter's gravitational scaffolding. Instead, they zip along like commuters late for work, leaving theorists scratching their heads. Then there's the opposite extreme, galaxies like Dragonfly 44, where dark matter dominates so overwhelmingly that stars should be tearing through their orbits like race cars, yet they move at a sedate, almost leisurely pace. These outliers aren't just statistical noise, they're glaring exceptions that challenge the very framework we've built to explain cosmic motion. So where does relativity falter? One possibility is that dark matter isn't distributed in the smooth, halo-like clouds our models assume. Instead, it might clump into invisible filaments or flow in rivers, creating gravitational hotspots that tug stars unpredictably. Imagine stirring coffee with a spoon. The liquid doesn't move uniformly. It swirls and eddies around hidden currents. Similarly, dark matter's hidden topography could warp galactic rotation in ways we're only beginning to map. But here's the radical alternative. Maybe it's not dark matter's fault at all. Modified gravity theories like MUND suggest Einstein's equations might need a tweak at galactic scales. Just as relativity refined Newton's laws for extreme speeds and masses, MUND proposes that gravity weakens less sharply over vast distances than we thought. Picture a magnet that's stronger at the edges than its shape should allow, a small adjustment with colossal consequences. In this view, galaxies' runaway stars aren't held by invisible matter, but by gravity itself playing by different rules when the pull gets faint. The stakes astronomical. If dark matter's distribution is weirder than we imagined, it could mean entire classes of particles are hiding in plain sight, their behavior rewriting particle physics. If modified gravity is right, it would be the first crack in relativity's foundation since its inception, a hint that even Einstein's masterpiece has blind spots when applied to the cosmos' grandest structures. For now, telescopes like the Vera Rubin Observatory are scanning the skies for clues, measuring galactic rotations with unprecedented precision. Each new dataset is a potential Rosetta Stone, decoding whether the universe's hidden hand belongs to dark matter's ghostly touch or to gravity itself, whispering secrets we're only beginning to hear. Time crystals shouldn't exist, not in a universe ruled by Einstein's smooth, flowing spacetime. These bizarre structures, which pulse in perpetual motion without energy input, were once thought impossible, violating everything from thermodynamics to relativity's notion of time as a continuous dimension. But when physicists created them in labs using chains of chilled ions and lasers, they stumbled onto something even stranger. Time crystals don't just tick, they fracture time itself in ways that defy relativity's elegant symmetry. Now imagine these crystals not sitting still in a lab, but hurtling through space at near light speeds. According to Einstein, their internal clock should slow down due to time dilation, their oscillations stretching like taffy. Yet early experiments suggest something far weirder. Time crystals in accelerated frames don't just slow down. Their rhythmic pulses become erratic, as if time for them isn't just stretching, but splintering into jagged, discrete steps. This isn't just a quirk of experimental design. Time crystals thrive on quantum coherence, where particles sync up across vast distances instantaneously, a process that should clash violently with relativity's strict light speed limit. When you accelerate such a system, you're not just testing time dilation, you're forcing quantum mechanics and relativity into a cage match where both theories emerge bruised. Some models predict that relativistic speeds could cause time crystals to decohere unpredictably, their perfect rhythms devolving into quantum static. Others speculate that acceleration might reveal hidden temporal layers, like peeling back spacetime to expose gears turning beneath. It's as if the universe has two sets of rules for time, one smooth and relativistic, the other granular and quantum, and time crystals are the first objects stubborn enough to demand both at once. The implications are dizzying. If time crystals in motion behave as unpredictably as early data suggests, it could mean relativity needs a radical update, one where time isn't just flexible but pixelated. Think of it like upgrading from an analog clock to a digital display. Einstein's theory describes the sweeping hands, but time crystals hint at unseen digits ticking beneath. This quantum chronodynamics could rewrite how we understand black holes, where extreme gravity warps time to breaking point, or the early universe, where spacetime's very structure might have emerged from primordial time crystals freezing into place. Yet the greatest twist might be practical. Time crystals are already being tested as quantum memory banks, their stable rhythms ideal for preserving fragile qubits. But if relativistic effects disrupt their coherence, it could doom dreams of quantum satellites relying on them for error-free communication across interstellar distances. Or more thrillingly, it might reveal workarounds, loopholes where quantum and relativistic time negotiate a truce. The answers could lie in future experiments with particle accelerators or space-based labs, where time crystals could be subjected to extremes no earthbound lab can match. For now, these paradoxical structures stand as both a challenge and a gift, a crack in physics' foundation where new light might pour through. Whether they force relativity to embrace quantum time or collapse under its contradictions, one thing's certain: the universe's clockworks are far more intricate than Einstein ever dreamed. Black holes are cosmic enigmas, swallowing everything that crosses their event horizons, even light. But they're not just vacuum cleaners of the universe, they are also unexpected particle factories. Scientists have long known that black holes emit Hawking radiation, a faint quantum glow predicted to consist of photons and other particles. Yet recent observations have uncovered something far stranger. Certain black holes are spewing out neutrinos, those ghostly, nearly massless particles that barely interact with matter, at rates that defy relativity's predictions. It's as if these cosmic behemoths have a secret assembly line, churning out particles that shouldn't exist in such abundance. The mystery deepens when you consider how neutrinos are produced. Normally, they're born in extreme environments like supernova or nuclear reactions, where energy densities are unimaginably high. Black holes, by contrast, should be neutrino deserts, their gravitational grip so strong that even these elusive particles should struggle to escape. But data from observatories like IceCube in Antarctica tell a different story. Some black holes, particularly those in active galactic nuclei, are surrounded by neutrino fluxes up to 1,000 times higher than models predict. It's like finding a desert oasis that's not just a puddle but a roaring waterfall. So where are these extra neutrinos coming from? One possibility is that Hawking radiation isn't as simple as we thought. The traditional view treats it as a slow, steady evaporation of thermal particles, like a pot of water simmering on low heat. But what if black holes also have quantum bursts, sudden eruptions where chunks of energy convert directly into neutrino pairs? This wouldn't just tweak the numbers. It would mean black holes have an entirely new way of losing mass, one that operates in fits and starts rather than a smooth trickle. Another theory dives into the black hole's accretion disk, the swirling maelstrom of superheated gas and dust that orbits the event horizon. At temperatures reaching billions of degrees, these disks could be neutrino powerhouses, with particle collisions so violent they spawn neutrinos in overwhelming numbers. But here's the catch. Relativity struggles to explain how these particles escape the disk's crushing gravity without losing most of their energy. Unless, of course, the disk itself is threaded with quantum tunnels, microscopic wormholes, or space-time wrinkles that let neutrinos slip through like ghosts passing through walls. The most radical idea, these excess neutrinos might be evidence of a black hole's quantum structure. Just as atoms have discrete energy levels, some models suggest black holes could have quantum hair, tiny, hidden features on their event horizons that influence how particles are emitted. If true, each neutrino could carry a fingerprint of the black hole's underlying quantum code, a message from the edge of space-time written in particles we're only beginning to decode. What makes this paradox so thrilling is that it's not just about particle physics, it's a potential window into quantum gravity. Neutrinos, with their ethereal nature and reluctance to interact, might be the perfect messengers from the black hole's chaotic edge, carrying clues about how relativity and quantum mechanics collide. Future detectors like the upcoming KM3NT in the Mediterranean could catch even more of these cosmic ghosts, testing whether the excess is a fluke or a fundamental feature of black holes. One thing's certain, if black holes are hiding new physics in their neutrino showers, the universe just got a lot more interesting. From quantum spookiness to cosmic expansion quirks, these 46 paradoxes aren't just glitches in Einstein's masterpiece, they're glowing signposts pointing beyond relativity's horizon. Think of them as cosmic breadcrumbs, each one revealing where the map of physics ends and uncharted territory begins. Take entanglement's spooky action, where particles communicate faster than light, or black holes that might hide fiery walls instead of smooth horizons. These aren't problems to solve so much as invitations to rethink spacetime's fabric, to question whether gravity is even a force at all, and to wonder if the universe runs on quantum code we've yet to crack. The real magic lies in what these paradoxes imply. Relativity isn't wrong, just incomplete. Like Newton's laws before it, Einstein's framework might be a brilliant approximation, a theory that works flawlessly until you push it to extremes. The singularity at a black hole's heart, the vacuum's unexplained energy, even the way galaxies spin too fast, all hint at deeper rules waiting to be uncovered. String theory dances with extra dimensions, loop quantum gravity pixelates spacetime, and emergent gravity suggests relativity could be an illusion woven from quantum entanglement. Which path will win? The answer might not be a single theory, but a mosaic, a patchwork where each paradox finds its place in a grander tapestry. What's thrilling is that we're living through this revolution. Telescopes like JWST and gravitational wave detectors are handing us raw data that could upend decades of assumptions. Lab experiments with quantum clocks and time crystals are testing whether time itself is fundamental or emergent. Even neutrinos, those cosmic ghosts, might carry messages from black holes about quantum gravity's secrets. The next Einstein could be working right now, scribbling equations that bridge the gap between the infinitesimally small and the cosmically vast. So here's the challenge and the joy of physics today: to stay open to the weirdness, to celebrate the anomalies, not fear them, because every paradox is a gift, a chance to ask better questions. Maybe the universe isn't just stranger than we imagine, but stranger than we can imagine. And that's where you come in. Hit subscribe to join us as we track these breakthroughs, from lab anomalies to galactic mysteries. Drop your favorite paradox in the comments. Is it the black hole information puzzle or the neutrino excess that keeps you up at night? The conversation's just getting started, and the next chapter of physics